Sorry.
All right.
That's what's your name? I have. Where's the one?
Sorry. Christine.
Oh, I'm sorry.
Oh, and I
Yeah,
can't.
you guys introduce yourself in here. Yeah.
Let's see, you're live and.
Yeah, we're live.
There you go.
Volume good?
Yeah.
Okay.
No, what's, she's got over there, we can do that too. There it is.
This is Shayla.
Okay.
Yeah, sorry, I'm Shayla. Shayla Corey.
Thank you, everybody, for joining. Oh, and I've got a microphone behind me, so you're going to be seeing the back of my head mostly, and I apologize for that. But let me fix that real quick.
Here's some plates, some bowls, and some spoons for the dips and stuff. And this.
There we go.
Just finished it.
Thank you guys for coming to the first light party for the new telescope. Being here, and I apologize for the sound. I'm sure it sounds like I've got the microphone to my back of the head. So here in about 3 minutes or so, and what I'll do is the plan is to start walking through like the telescope and explain what's going on, and then proceed to actually some imaging and just explanation of what's going on and how astrophotography is done these days. Corey.
Sit on the couch.
Shayla? Shayla.
Okay. Do you want me to get it?
We've been running around all day like,
Oh, no,
inhaling cleaning products.
You're loud.
Oh, sorry, hon.
We're streaming.
Okay.
Oh, by all means, yes.
And then you got to do what they want and I keep.
Oh, by all means, we'll stand up.
Okay.
All right.
Big, so that's be better for students. This one nice. So that's what he's ready for.
Doesn't matter. I let everybody know we're starting in just 2 minutes here.
It's okay. We've got 2 minutes and then we're gonna have to pay attention and listen if we want to know what's going on. Shauna, do you want to go water or Sprite?
Tom,
I got you a Red Bull.
Oh, thank you.
Maybe you want a beer, maybe you don't.
It's gonna be one of those nights. Thank you so much. I'm triple fisting.
Yeah, and then here's just
Is this part of no, that's just where it is right now, and I don't know what is it? So that's our projector. We have a few. Guys. So how many telescopes do you guys have? I think we had 2 older ones, and they're somewhere over here. I mean, they're old telescopes.
so.
What's up, hon?
Telescopes.
They're underneath behind the garbage cans.
Oh, of course. Oh.
Just where you should keep telescopes. Doesn't everyone keep them behind garbage cans?
So cool.
One is like the both of those combined, like one's
Bigger than that, actually.
It's pretty dark out there.
And I'll go through it, but the telescope that's out there is actually 4 feet
Well,
long.
I'm gonna grab some snacks.
4 feet long and 14 inches in diameter.
And sit down, because in 2 minutes, he's gonna start explaining all of that.
Okay, it is 7:30. We are going to start here. So the first thing I wanted to do was bring up I've got an image of the scope here, and just a quick explanation as to what you're looking at here. So this is a reflector, which means that the original scopes that were created back in the 1800s were refractors. And what it was is it was the typical, like a binoculars, like one side of a binocular. So you've got lenses set up and the lenses curve the light and focus it down to your eye. So this is an SCT and it's a reflector. And what happens is the light enters at the black end here. This black end here, this entire thing is actually a dew shield. So it's part of the telescope, but what it does is it keeps everything contained and eliminates it from cooling off, so dew will form. And of course, if dew forms on the lens, you suddenly can't see anything out of it. So there's a lens right here. It's actually technically a corrector plate. It's actually not a lens technically, but the light comes in from the front, comes all the way down here, bounces off a mirror here on the back, reflects back up to the front. Now there's two configurations for this telescope. There's like a zoomed in configuration and there's a Hyperstar configuration. Tonight we're playing with a Hyperstar configuration. So underneath here is a camera and another series of lenses. So you actually couldn't look through this telescope at the sky because the imaging is all done here. And obviously you'd be in the way of everything with your head in there. Now, the other configuration is where the light comes in from the stars, goes down, reflects off the back, and then comes up to a center. There's a mirror in the center here that it bounces, and then it comes all the way back down again and exits out the back. And then you would put a camera back here, and that's a zoomed in type mode. So, and I just got a pop up here. Let me just kill this in a second. Don't know why that's popping up. Of course. So, okay, so this telescope is 14 inches in diameter. The larger the telescope diameter is, the more light it gathers that comes in at it. So this is thousands of times more sensitive than your eye is. And then on top of that, when you put a camera on it, you can now do long exposures. And with the long exposures, it can see far beyond what your eye can see. So even if you were zoomed in, or I'm sorry, if you looked through the telescope, you would not see this camera to do that. So I've got an image here of a Hyperstar setup, which is right here. So this is that front of the telescope where the light enters and it goes down, bounces off a mirror at the back, and then comes up through. This is called a Hyperstar right here. This is the camera. So these cameras are specifically astrophotography cameras. There's a whole world that I could go into explaining how because everything is dependent on everything else. This setup is black and white. So we'll go into the differences of what that does. But first thing I want to do is I want to get the telescope active. All right. So I have a remote desktop. So I have a second computer. So the computer that we're seeing here, the computer in this desktop is actually sitting right next to me, and it's for processing. It's got the image software on it, video cards on it. It's got a very high-end CPU on it because it takes a lot of work to process these images. The images that I'll pull up, just for an example here. So Veil Nebula, just my calibration images. So this telescope, it's not something you just set up and walk away from. It's taken me about 2 months to get everything calibrated and working right. It's not a normal process. So in this, I've got Veil Nebula. So just the calibration images that I've taken for this. Oops, sorry. Popped up on the wrong screen. So 160 gigs worth of images. So tremendous. But each image that the camera takes is 120 megs. And what happens is that again, even like I was talking about how your eye is so sensitive and the camera is more sensitive, you take multiple images all night long, and all those stack together to form an even more impressive image. So, and we'll talk about all that and everything. But so I'll kill this. And what we'll do is we will move over. Now, this computer is out at the telescope. This is physically connected up to it. So I'm just going to walk through the startup here. So what you do is this software, when it opens here, is the actual software that controls the mount. So the mount is all computerized, and I'll just drop down here. We'll go back to the image here. So this mount right here is all computerized. You can't do any astrophotography without a mount, because what it has to do is it has to track the stars as they move across the sky. If you just set up a camera, click the shutter, and have it open for about 20 seconds even, you'll start getting star trails. And I'm sure you guys have all seen those images that you know, all the stars are circling around the North Pole. So that's what this mount does. And there's counterweights on it to combat this, and to keep, you have to keep everything balanced, keep the mount from working too hard. So that's what all of this is. And over here, this is a guide scope, and we'll go into that. And this is an autofocuser right here, and we'll go into all that. And right here is actually a fan that blows air through the telescope to keep the temperature the same, because temperature differentials, and suddenly you get bad images and so forth. So we'll just click back over here. So this is the telescope mount software. Let me zoom out on it. So this is a view of the sky. You're looking north at Polaris. And first step is to connect up to it. Watch, it doesn't work. Hey, okay, so it's coming up here. It's basically finished finding anything. So normally, if you have a telescope on a tripod and you bring it out, you again have to calibrate it. Now, I've worked to make sure that this is pointing due north within a fraction of a degree. So I've got star sense on this. So what it'll do is there's actually a camera attached to it, and the scope will move around the sky and take images, and then compare those images to a database. It has to know where it is and know where the pointing is. And it basically gets its bearing. It makes its own map. I don't have to do that. So I can just do a quick line, which basically says, trust me, it works. So you see it. So now what it's going to do is it's got home switches. So the telescope is going to move to a predetermined position so it knows where it's starting from. And that's what it's going to do right now. And you'll watch this will wiggle around a little bit, the little pointer, as it tries to figure out what's going on. So it takes it a second.
So outside, it's actually moving.
Oh, yeah. Yeah. Right now, that telescope is moving all over the place.
And it's trying to find something it recognizes?
It's got some switches inside. So what it's doing is it's rotating up to one. So it's got two axes. The telescope has two axes. So if it's pointing at the North Pole, it's got a basically an east-west and a rotation. So what it did was it rotated so yeah, let me actually, instead of just saying it that way, let me just show you. So these are the two axes. One axis runs through here, and one axis runs down. So basically these weights are at the end of one axis, and the other axis is over here. So what it's done is it's moved itself upright to basically in this position, but then this axis right here rotated around so the telescope would actually be pointing away from you. North, we're actually looking north. So right now the telescope looks like this, only the whole thing is rotated around. So we'd be looking in this picture at the back of the telescope right here. Okay.
But we're not seeing anything yet because
Haven't even gotten there yet. So
okay.
we've got a dew heater, which this automatically takes care of temperature, knows what's going on with the outdoors. And if dew starts up, there's a ring around that front glass that heats up to keep dew from forming on it. We've got the power is turned on and everything looks good. So we're basically done here. So next, and it's going to go cancel. Why did it do that?
I have a question. Do you choose where to point it?
Oh yeah. And we'll get fully into how I choose and what tools and everything. That's when it becomes fun. So let's do a perform alignment. I must have clicked the wrong button. There we go. Okay. I hit the wrong button. So now it's just doing a quick thing to an initial position. There's a thing called a PEC. It's called periodic error correction. We won't go into it, but basically these telescopes have little errors in the gears. And one of the calibration processes is letting it know. It watches the sky as it rotates and it goes, oh, I need to speed up a little bit here when I get to this gearing spot. So it's just computerized stuff. So we can close this software now. So the telescope is hooked up. It's ready to go there. So now we're going to open up. This is called the guiding software. And this software, although it looks like I'm fighting in some space battle, what this really is this has a little telescope. Let me just connect here. Okay, so we're connected. So this has a little telescope and it will, it's this right here. So it's this little camera on the back looking through this telescope. And what it does is it watches the sky and a star. And if that star moves, it just tells the telescope, no, go back the other way a little bit. So it keeps the telescope pointed in exactly the same spot. Because if you got your imaging camera imaging, it cannot use that image until it downloads it. So if I've got a 10-minute exposure going on, it's looking at it for 10 minutes and the telescope mounts aren't perfect. So the star will be moving a little bit. And what this guide scope does in this software is it keeps it at exactly the right spot by telling it, move a little bit, right, left. And that's what these are. These are up, down, left, rights moving. So we're just going to start that camera. And right now it's set to just 2-minute exposures. And I don't care that I don't have dark frames. So these are stars through that telescope. So if I were to select here, so these are all stars that it sees. And I can actually start the guiding right now. And so what it's doing is it's tracking this spot. So I can clear the results here. And you can see that it'll take it a minute to kind of settle in. So I was talking about those two axes. The red is one axis and the blue is another axis. So we will let this see if I have to, I probably have to calibrate it again. And it automatically will calibrate itself. So, okay. So what I can do here is I'm just going to stop it. And we're just going to go to tools here. I'm going to delete my calibration. And we'll just kick off the calibration here. And you can see what it's going to do here is, so, you know, it's doing west steps, east steps, north steps, and it's recording what the distance is. So we'll just watch this to make sure it's going. It's not going.
The sky is broken.
Yeah.
The sky is broken.
It's not. It's doing it again.
So can you like pick out constellations and see them? Up close?
To a point. Let me, something is once again wrong. I'm not uninstalling or installing. Let me try it can be a very frustrating hobby.
I sense that.
Yes. So let me try it again. Okay, let's see if it'll calibrate. Will it jump in?
So outside, it's just standing still.
It's about to move. So wants to calibrate. So I'm going to go. So there are certain spots in the sky that the calibration is more accurate than others. So right now outside, in fact, I can pop this software up and you can see that the telescope, let me just put it here so it tracks it, is moving to a different spot in the sky. And what it will do is when it's to that spot, it will then calibrate, because right now that camera, that guide system doesn't know if I tell the telescope to move right, does it actually move right, or does it move left, or does it move up, or does it move down? So this is basically keeping track of that or learning that. So before I actually give up on this.
Calibrate, define, retrieve, learn your points.
Yes, it learns when I tell this telescope to move. It doesn't, we have up, down, left, right. It doesn't. It just knows I've got 4 directions. So when I tell it to move direction 1, what direction does the telescope move? When I tell it to move direction 2, which way does it move? So it's just learning that. It's also going to learn how much does it move when I tell it to move. So we're going to go back to the other method here real quick.
Is this like pre-programmed or did you build this?
No, this, I did not build this. This software, you can, most of this is actually free software. So let me try this again. So we're going to go in here. So we've now, okay, why am I having, okay, let me try this again. All right. So we are connected up to the camera. We're connected up to the mount. Close that. It didn't like the fact that I just changed that. So we're just going to go to tools. We are going to clear our calibration data again. Start taking images. So it's going to select stars. So you can see the stars are different here than they were before. And we're going to, okay, so here we go. So now it's gone to west step. There we go. Now it's moving. So you can see the distance is 2.5. And if you look up here, you can see the star moving off. This is just a zoomed in image. So the mount is, the camera and the system is saying, move direction 1. And it'll move it that way a little bit. And then it'll move it back. And it'll say move direction 2. And it's just so that it knows what's going on. So we're going to let this do its calibration. And now we're going to launch this software. Well, it's already launched, called N.I.N.A. So this software is what controls everything. This is the brains behind everything. So I'm going to connect all devices, and it will connect up the focuser. It will, so the whole thing auto focuses, the whole thing auto everything. So you can see that it's connected everything up. It doesn't like the fact that we're, it can't tell the mount what our elevation is for some reason, and it's fine. It doesn't matter at all. So what we've got here is we've got a camera, and this is a black and white camera. And the advantage of a black and white camera is your phone, any digital camera that you have, each pixel on the camera does not know what color it is. So if you have just a pixel and a photon comes into that pixel, it has no idea if that's a red photon, a green photon, a blue photon, no concept of what the color is. The way it knows is in front of those pixels, there's a filter, and it's called a bare mask. So there's in front of the chip, there are literally lots of teeny tiny filters that go all the way around, but a pixel can only have one filter in front of it. So pixel 1 could be green, pixel 2 could be blue, pixel 3 could be red. And it just repeats this over and over again. So you can see that pixel that has a green filter can only detect green. My black and white camera, every pixel can get any photon. So what I do is I insert a large filter for whatever I'm looking for in front of that. So if I want to capture, instead of taking one color image like you would do it with your phone, I take 3 pictures, one with a red filter, one with a green filter, and one with a blue filter. And then those get combined together to form a color photo. And I'll show that. But so we've got a camera, it's connected up. In fact, let me just go to the sequencer and kick this off so it does its thing.
Does it say CYMK or RGB?
RGB. And in fact, the beautiful thing about it is you tell it what you want. So narrowband imaging is, and we'll talk about that too. Yeah, I don't just put a red filter in. I put a filter in that just detects ionized hydrogen gas or ionized oxygen or ionized sulfur. And you can actually start doing like scientific, when we'll show that, I've got all sorts of sample images. So I've started this sequencer, and this is kind of a program. Let me kick over to a spot that's a little easier to see. So right here. So what we have here is this is like a script that runs. So it starts. I don't care what the filter is. It doesn't matter. So it waits until, and in this case, I've got it waiting until nautical dark. It's a little bit before you can take imaging, but it's dark enough that we're getting close. We got 20 minutes or so. So the camera, then when nautical dark hits, then the dew heater turns on. So there's a heater on the camera in case, and there's a that has a dew heater that warms it to keep any kind of dew from forming. Dew anywhere in the system means you get blurry images. So the dew heater's turned on. Right now, the camera is cooling down to -10 degrees. So what happens is there's two things that happen. When you've got a camera taking images, and especially with something along this line, heat or the warmer the camera is, heat emits light. And you've all seen like the firemen in the dark and stuff, and they've got that camera that shows the infrared. Infrared are photons. These cameras will detect infrared. So just it's called black body radiation is the name of it. But just we are constantly emitting light off of us because we're warm. And by cooling the camera down, I'm doing two things. I'm limiting that amount of light. But really what I'm doing is I'm bringing it down to a consistent temperature. And that consistency means I'm getting the same every single time. So in winter, I'll probably drop it down to -20 or -30, depending on what the temperature is outside, and it just keeps it even. So you get the same results every time. So this camera is cooling down. And in fact, we can kick right.
Nautical dark, defined.
Nautical dark is essentially dark when it's dark to you and me. You know, when you turn on your headlights and that kind of stuff. Then there's astro dark, which is defined by the sun a certain number of degrees below the horizon. But that's when you can really start imaging, and you don't have, because these cameras are so sensitive, you don't have the light, in the atmosphere. So right now the camera is down to 2.3 degrees, 2.1 degrees. And I can see that it's got 32% power. So it'll slowly keep cooling itself down here. Now, while that's going, I can kick back over to the sequencer here. And we can see that it is right here. This is running. So the idea here is that I can start this and leave. I don't have to be present for this thing to go out, image all night long, and shut itself down in the morning. The whole thing it's a robot. It'll do whatever I tell it to do. And that's also one of the pains in the rear, because it's so easy to mess it up. I can't tell you how many times I've come out, even doing the calibrations, and you see the image and there are just stars scraping across the screen. There's red errors going up the screen. It's frustrating, but when it works, it's amazing. And when it doesn't work, it's my fault. I've done something wrong. So we've got a few minutes to go on this. And so at 8:17 is astronomical dark. And that's when the real fun begins. So now if I want to image something, so we were talking about that, how do I decide what I want to image? There's a bunch of different ways to do this. Okay. I can see an image that somebody else took of, one of my favorites is like the Rosette Nebula or one of those. But because we're going around the sun, half of the year, the object that you may want to image is on the other side of the sun. So it's only visible during the day when I can't image. So you've got time of the year, you've got altitude above the horizon. So the less atmosphere I'm looking through, the better it is. Atmosphere is my enemy. That's why Hubble is out there and James Webb Space Telescope. They've got no atmosphere. Those stars are teeny. They're like nothing you've ever seen. They're literally pinpoints. And they're so powerful and they're so zoomed in that I can't image that because of the sky. It's impossible for me to get anything even remotely close to that incredible detail that they get. And I can bring up some kind of comparison. Every astrophotographer ends up posting up like here's Hubble, here's mine, because we're always impressed when we get something even remotely close that's even comparable. So the imaging I do mostly is wide field. And that's what that Hyperstar, I was talking about those two configurations. Hyperstar gives me this giant wide view of the sky. That's just absolutely incredible. Just make sure nobody's, no text. Nobody's like, Tom, we can't hear you. Oh,
Do we know how many people are watching?
5. So I can go to Sky Atlas, and what this software does, I can tell it, okay, I want to image a nebula, and I want it to be this high in the horizon during this time. So I can fill in here and say that, let's say for altitude, let's say something 40 degrees or higher. So that gets it fairly high up in the sky. And then I can say from astronomical dusk to dawn, I can do. But yeah, let's start with this. This is fine. So I can choose how big it is, where it is in relation to the moon. I can do, this is a favorite of mine, an object type. So let's look at planetary nebula are very small. So let's do a bright nebula. Let's search for a bright nebula. All right. And come on, minimize, please. Thank you. And then you can do in constellations, coordinates, all sorts of criteria here. So I'm just going to tell it to search. And it's going out to the internet and it's pulled up all of these objects. And what it's doing here is it's telling me when it's high in the sky. So you got dusk. Oop, why did you just do that? I just broke it.
It's AI. It does what it wants.
It does. Why did you just do that? Okay, we're going to try that again. Let's just search again. Okay, it's back. Okay, so without me screwing this up again, so you can see these top ones here. This is right now basically, and you know, this is dawn over here, and you can see that most of these are high in the sky near dawn. I don't want to do that. That's not near now. So this one right here, this is high in the sky, right? Essentially now, we could image this right now if it gets dark. So what I can do is I can either add it to my sequencing, but that doesn't give me an idea what I'm looking at. So what I can do here is say, set it for framing. So this will let me choose exactly where, and we'll see here in a second, exactly where I'm pointing, exactly what I'm looking at. So this,
The bigger the little.
exactly, it lets me choose the exact spot. It takes a minute. It's going out to the internet. It's pulling down an image, and there we go. Okay, this is one of my favorite targets. You will see me post images of this all the time. This is the Veil Nebula. Okay, this is, I think, the most beautiful thing in the world. In fact, if you look at the screen here, this is going to be that. So you see here the long sliver with the star, the nebulosity with the star, and if we go here, there's that nebulosity with a star. So I can now take this and move it around and frame it however I want it to be. So normally I go for something like this. And let's say I'm like, let's see, it's too big. I want to grab that stuff down below. I can actually tell it, do multiple exposures. Come on. Oops, I moved off of it. So it will do 4 different spots, and then I can combine it together later in software to make one giant image of this. But we're not doing that right now. So once I say, yep, this is where I want it. This is what I want to image. Maybe I want to do the whole thing here. Maybe I want to focus over here. But whatever it is, I can then add that specific spot to the sequencer, and it kicks it over to here.
So that was an image from the internet, but the one with the color in it was one.
That's one of mine. Exactly.
That's great.
Yeah. So this is what I do. And we got all sorts of mood stuff. It just turned on the AC in the bedroom. Would you do me a favor and turn it off for me? All right. So the other way to image it, what do we got here? 2017. So we are waiting 17 minutes and 38 seconds for it to kick off. So I have this software too. It's called Stellarium. There's a couple of different programs out there that will do this, but this is another way for me to figure out what I want to image. And this lets me plan days in advance, and I can create these scripts and save them and then, you know, bring them back later on. It's annoying software. A lot of time it locks up the computer. Okay, it's not locking anything up. Good. So, okay, so this is again a view of the sky. So let me zoom out a little bit. So we're looking southwest. So you can see all of this stuff right here. This most of the interesting stuff to image is in the Milky Way. So the folks on the stream probably do not are those folks are in the city. So, but for us, you can look up and just the Milky Way is so obvious here, right? That's why you'll see all of them in this narrow band coming across. So what I can do here is, like we were just looking at the Veil Nebula. I know that is going to be right in here. There's the North American Nebula. So I can choose, like, what do I feel like tonight? Like Elephant Trunk Nebula. That's a good one. So I can double click on it and zoom in. But this software knows about my telescope. So I can just click here. And there's the Elephant Trunk Nebula. And the red mark shows me where the camera is. And if I decided,
And this is live.
well, this is just software. And I can change the time. Like I can actually speed up time to see where things are going to be tomorrow or the next day or what's going on. So, oh, and there's a satellite going across. So, and this is live right now. I mean, this is our current time. So this is what we would look at right outside, but it knows my telescope. So I can go, I don't really like the way that looks with that. So I'm going to change it to the other telescope. And you can see here's the red box right here. So this is a really zoomed in view with the telescope. And that's the bigger view of the telescope. You can see the red box is here. And then once I've got the object picked out, I can then go back to my software here, go back to my framing assistant, and I can actually say, get coordinates from the planetarium. And I click the button and it is now going to that software saying, where were you looking? And it's now going to go out to the internet, pull the image to that object and bring it in here. So I can now say, this is what I want to image for tonight. And by the way, the reason we're not imaging right now is it's still too light out. So we're waiting for everything to get set up. So this is the Elephant Trunk Nebula. And I can now move this around anywhere I want to. Yes, it's in the Milky Way. And I can then send it to the script and say, put this into my set to image tonight. I'm actually not so I've seen it enough. I don't know why this is here. That's a plane.
What?
These marks going through here, this is a plane. It's the two lights on the end of the wings and then the light in the middle. I've seen it so many times on my images and sworn at it that, you just learn what these things are. So anyhow, so this is how I choose what I'm going to image. And I can tell the script, I want to image this, and then I want to image this, and then I want to image this. So we're going to kick back over here to our guider and just make sure, yes, that's looking beautiful. Okay, we are calibrated. So you can see, so this right here, this ring is 1 arc second. If all the dots are within this ring right here, so the middle one is a half arc second, this is a full arc second. If everything is within an arc second, you've got everything, you're sitting beautiful. 1 arc second is the amount of the stars move in 1 second. So they're constantly moving. You can't see anything in 1 second. So that's how sensitive all this is. And what you're seeing here, so this image right here is the full image that the camera is capturing. You can see each of these circles is a star that it's watching. And this one in the crosshairs is the one it liked the best. And what it's doing is this is the one you're seeing over here. And so you're seeing this is how clearly defined the star is. The sharper this spike is, the better it is, the smaller and more precise it is. The smaller and more precise it is, the better off you are. So this is each frame, each picture it takes, it just tells you how far off it is. And then this graph down below, the red, the solid lines, the red and the blue are the right ascension and declination. The red is the declination, the blue is right ascension. And really what that is that's the left, right, up and down. So, so it's showing how far off that is, which is basically the same thing you're seeing over here. And then these bars that you see, this is the instruction to the telescope, move left, move right. And how big that bar is determines how much it asked it to move. So a little bar, a little bit, big bar, a lot. So this is actually not great. So you can see that my total error here is just a little bit over 1 arc second. With work and with continuing, I'll get that down to probably half an arc second. At least that's what the goal is. So this is the basic what's going on without going too deep into it. So what I've got in there right now is I have what's called a luminosity filter. So the filter allows all light through except infrared and ultraviolet. So it's blocking the either side, and basically all light that we can see is being recorded. And when it kicks off, they're very bright. Like with the size of this telescope, with the camera that I've got, it's called a full frame sensor. And like I said, each image is 120 megs. And the obviously the bigger the sensor is, and there's pixel size, there's all sorts of mess to get into that I don't want to get into for this. If anybody on the stream has questions about this, I can fill you in on it. Let me just make sure. So, all right. Sorry. Let me hold on a second. It's a party. I'm supposed to be drinking. Okay. So let's get back to the software here, to where the fun begins. Okay. So just a run through here of the software, just so you know what you're looking at. So the equipment image page here, this is actually the equipment. This is where I tell it the guider, point to this software. The mount, that it's the CPWI, where it's Celestron. It's the Celestron software to control the so because what this is this software control all sorts, no matter whose mount you get, you can control it with this software. So it's the translation and telling it where to go to get this stuff. So we got a telescope, we got the guider, we've got the mount. There's a rotator, which is very cool. What it will do is when you're framing things here, this square, I can rotate it around and say, I want to image at this angle. And what the rotator will do is literally rotate that camera so that it positions everything exactly how you've told it. I do not have a rotator. I am not that fancy yet. But so I'm basically, when I tell it where to image, I'm just telling it the center spot. It doesn't know what orientation. It knows, but it's like, I've told it, I don't care what the orientation is. We'll deal with that later, sort of thing. So that's what a rotator will do. And then we've got the autofocuser, which we'll see, and I'll talk, and it's very cool how a computer could actually focus a telescope far better than we can. There's no comparison between a computer with the focus and with your eye, and you'll actually see how that works. It's truly incredible. A filter wheel. I don't have a filter wheel. You don't install a filter wheel when you're using the Hyperstar, because what happens is too much stuff is that camera was in front of the lens, right? And it's what I was talking about, how if you were to look through, if you put an eyepiece there and look through it, you're blocking it because the light is coming from behind your head. And a filter wheel will do the same thing. So what I've done is I've told it it's a manual filter wheel. So I still have the ability to tell it, this is a luminosity filter, this is a red filter, this is a whatever, yeah. So I can give it the details because it needs to know that to put into the files. And I'll show you guys that all later. That's very cool. And then we've got the camera. So those are the main components that are electronic that it's controlling. So that's what this first one is here. And then of course we've got the Sky Atlas, which we were talking about here, where it can choose targets. And then I've got the framing assistant, which we've talked to, where I can choose and pick the exact spot that I want it to image. We're not going to go into the flats wizard. This is calibration type stuff where it will take certain images. Everything in astrophotography is about getting rid of noise. So it will take images with a lens cap on so that every camera has what's called dark noise and dark current technically. And so if it takes an image in the dark, it can then, so say in your camera, you've got a pixel that's broken. It happens to every camera. It's not a big deal, but you're not going to have like a bright spot. If you take a picture of it with a lens cap on and you've got a bright spot, the system goes, oh, that pixel's bad. And it can literally mathematically remove that bad pixel. So it compensates for things like that. There are dark frames, there are flat frames. So if you have dust on it, when you can take a picture of like the sky with no clouds and it'll make like a little donut. And the system will now know, oh, that donut's not supposed to be there. And it can mathematically subtract that donut out of your real images. So those are all calibration frames. Now we've got the sequencing where I've got all the things over here that it can do. So I can choose, I can tell it, I want to switch filter. I want to, in fact, I literally just drag them over. So if I wanted to have it autofocus after X number of exposures, I can just drag it over and drop it right here into the trigger and it will set that auto exposure. And you can see I've already got a bunch of that stuff. Let me, so we've got, where are we here? So yeah, we've got 5 minutes. So this is the beginning. So it starts here. I've told it, in fact, I'm going to do this. I'm going to switch this to luminance, not that it matters. So it waits for the time, turns on the dew heater. It's cooling the camera. That's already done. And now it's waiting for astronomical dark. When it's done with astronomical dark, it'll unpark the telescope. When you park the telescope, my telescope is so big that when my dome closes, when my observatory closes, it would close on the telescope. So I've told the telescope, I want you, when you're done, to go into this certain position where it's pointed down. So when the roof comes and closes up on it, it doesn't close on the telescope. I still have a lot of fear regarding this, by the way. I don't fully trust this yet. So, and then it'll find home and then it'll start the guiding. And now it starts the Veil Nebula. I've taken it from the framing assistant and sent this here. So it's got all the information on the Veil Nebula. Here's that same graph. So here's now right here, this little dotted line. So we're almost at astro dark. And then, it knows where it is. So after that's done, it will now come in. So triggers are things that happen once in a while. This is when to start and when to stop. And these are the instructions. So what's going to happen is it's going to come into here. It's going to switch filter to whatever the filter is, because I have to, even though I'm not switching a filter, the software has to know what the filter is that it's imaging through for processing later on. It'll run an autofocus. It'll slew. Slew is what's called when the telescope moves to wherever it needs to go. That's slewing. And then, so after it slews, it will actually take a photograph, and you'll see this. It'll take a photograph of the sky and compare it. It's called plate solving. And it's called plate solving because back in the 30s, when they were astronomy, they knew that looking, just like we do, that looking through, you can see some stuff. But if you hook up a camera to the back of it, you can see a lot. Back before Kodak was, actually Kodak was probably involved with some of this, they were glass plates. So back when you see the old school cameras, instead of putting the emulsions and the chemicals on a piece of essentially plastic, it was on a glass plate. And they would put the glass plate in and expose that glass plate. And that's why it's called plate solving, is that it was the photographic plate compared against a known map of the sky, and you could see exactly where you're pointing. This does that automatically. And if it's off from where it thinks it is, it will automatically move the telescope to the right spot, retake a picture, and make sure, yes, I'm pointing in the right spot. So if I were to go out when it's imaging and move the telescope a little bit, it'll be like, wait a second, you're in the wrong spot. You need to be over here. So it'll do that, and then it'll take a bunch of exposures, and then it'll redo this loop over and over. And then these are the things that it does once in a while. So every 5 exposures here, it does a thing called dithering. Just moves the telescope just a little bit. And what it does is it keeps all the pixels from being in the same spot. So what happens is, and there's some debate to this, won't go into it, but what's happening is you actually, by moving the telescope around just a little bit, mathematically the software can actually get more resolution out of that. And if you have, say, a speck of dust that you haven't gotten on a calibration frame, you're moving that speck of dust around and spreading out the bad information all night long instead of that bad spot all night long in the same spot, because then it'll show up in your final image. So you're doing all these things to get that image just perfect. So after every 5 images, it'll move it a little bit. So I've got this set to autofocus, and we'll talk about the autofocus. It tells the size of the star. So if the star gets kind of big and puffy because it's out of focus, it goes, wait, and it re-autofocuses again. And after every 20 exposures, it will do another one of those plate solvings. It'll just do a safety, like, am I still pointed in the right direction? And the meridian flip is a scenario where when the telescope gets up to the meridian, which is due overhead, so you've got the zenith is straight up, the meridian is a line that runs from the North Star all the way south. When the telescope gets up to that angle, the back of the telescope, there's a pier it's on, the back of the telescope can hit the pier. So what happens is when it gets up, it goes, oh, I got to stop imaging. So if it's facing east, it goes up, gets to the spot, and it goes, okay. And it recenters, turns the other way, and then comes up from that side. So now it can go all night long without the back of the telescope hitting the pier. So that's a meridian flip. It's a royal pain in the butt to get set up. And then it goes back into its imaging again. Where are we going? Oh, 5 seconds, 4 seconds, 3 seconds. All right, let the fun begin. So here we go. All right, so waiting for telescope. So it's going home. So we can just click over here real quick. And there it goes. So it's going to its home position now so that everything knows where it is. And I could be, in fact, we went out to dinner down to town, did all this on its own. I don't have to be anywhere around this. In fact, I can control this from anywhere in the world, which is really cool. So it's gone and it's pointing to the North Pole again here. Okay, so it's at the North Pole, and you can see this I can just click over here to the guider and everything has moved around. It stopped guiding. It knows that it's moved around to there. All right. And it's starting guiding again. All right. So what it'll do is now it'll chill for a second because everything has to be, when you move things, when you autofocus, there's a settling time. All right. So and now it's calibrating the guider, which I didn't really want to do that actually. So you see, mistake on my part. So it already calibrated and now it's calibrating at the North Pole, not the place that you want to calibrate. So it's just a continuous learning experience. Yeah. So it's calibrating again. Oh, shoot.
So unless it's perfect, it's not going to shoot an image.
No, it'll shoot an image. It'll just be a bad image.
Oh.
It doesn't. It can. I mean, see, I'm one of those people. It can evaluate the image and know that there's something wrong, but it's still going to shoot the image. This actually, I don't know if this is going to calibrate okay. It might be okay. So anyhow, so what I need to do is I need to modify this. So this is part of that process. So I've been doing this for a month now, getting this set up, and I'm still learning, like, oh crap, I did this wrong. And because I got to wait until the next night basically to rerun through the sequence again, for the startup sequence. So my startup sequence, I've been having a lot of trouble with the guiding.
You mean your startup sequence is at nautical dark and it only can happen then?
I can trick it a little bit, but there's something about running it for real that you catch stuff that you normally don't, basically. So like normally I would be like, don't go back to the home position. But I just discovered that this is a problem because it went to the home position. It's like, I need to calibrate. So, oh, this is going to be horrible. So yeah. So what's happening is it's telling the telescope move, and it's only moving a teeny, tiny bit because it's pointed at the North Star.
It's too far away to image.
Well, it needs to be, to get a good calibration for your guiding, it needs to be pointed more, not at the North Star. It needs to be pointed kind of at the middle, because that way each movement is dramatic and full direction. When you're pointing at the North Star, one of the directions. So if I have something that's rotating this way and I'm pointing this way, the rotation is big. If I'm pointed at the North Star, the rotation is this. So right now it's moving it, but it's just doing this. And it's like, it's not moving very much. Yeah. So that's why, like, it's moved a distance of 0.8. It wants a distance at 20. So I'm killing this. I am stopping the calibration.
But we're in nautical dark, so we can do it again.
Well, yeah. And I can, it doesn't matter for this. It doesn't matter if it's calibrated well. So I've killed the calibration. It's already freaked out on me. So no big deal. So I'm just going to pop up here. So we are going to end this, and we are going to just, basically, I'm going to trick it. So we've started guiding. So hopefully, no. Yeah, I don't want you to retry. Okay. All right. So I am going to stop the sequence, and I'm going to just tell it, don't do this. So where are we? We are start guiding, force calibration off. So I'm basically telling it, don't calibrate. We are going to skip this for now. So stop. All right. And let's start it.
Tom, some background. You didn't learn this overnight. You've been at
Years.
Yeah, just so that us
Yeah.
that are
Years.
looking at it for the first time don't feel like we're so small.
To 2015 is when I started, and realized we moved here for this exactly.
Because I'm thinking, okay.
Yeah.
I'm going to go to remedial school.
So it's freaking out a little bit. So what I'm going to do here is I'm going to resend it back to its spot.
That's what happens when it looks wrong.
All right. So what I'm going to do is I'm going to tell it where I want to calibrate. So what I'm going to do is I'm just going to move here. Oh, sorry. Here we go. Okay. So this line right here is where the best calibration happens. So I'm basically going to tell the scope to go there. And then we're going to,
What'd you choose?
I just chose a star on this purple line because it's halfway between the north and the south, basically. Actually, that's not accurate, but actually it is. That is accurate. It's halfway between north and south. So if you look at this, you've got North Star right here by Polaris. This is the zenith straight overhead. And then this here is halfway between the North Star and the equivalent south direction. So it's moved there. We're good. I'm going to jump back to the guiding software here because it wiped out the calibration that I had done. And it's, you know.
So can you find like Saturn?
Yes.
Can we see Saturn?
Saturn is not up until about 3 in the morning.
Oh.
Trust me, I looked at all the stuff. I've been looking for days about what's coming up tonight. So we'll get,
That's why you chose October 5th.
I chose October 5th because I got luck. The monsoon season, it was months, 2 months with cloudy skies. I mean, and so now it's coming up. Basically, this was the first clear night when I was feeling good about it. And I knew that this was I'd calibrated and gotten everything good enough. So now you can see that star's moving way off. I know I don't have any dark frames. It's okay. So you can see it's moved a distance to 26.9 in just a few steps. We let it sit there for a couple of minutes. Well, not minutes, but quite a while, and it only moved 7. So this is a much better calibration. So, oh, it's already guiding. That was terrifyingly fast. Oh, no, okay, close. Let me calibrate that again. It must have actually been partway through the calibration. So I'm just going to go here. Oh, sorry. Stop it. And you can tell that red flashing is it going, you're out of your mind. Something's wrong. So we're just going to go up here. If I can find my mouse. Where'd my mouse go? There's my mouse. Okay. And we're just going to tell it, delete out your calibration. Okay. And we're going to tell it, start taking my images. There we go. Find the stars. There are stars it likes. Start guiding. It knows it has no calibration. So here we go. So we got west step 1. So it's giving it 1 nudge to the west, 2 nudges. We're already at 9. 3 nudges, we're at 17. So you can see that this star is moved dramatically off. And here it is right here. And you can see it moving each step.
It's so interesting to see how fast it like moves on this. You know, because you never think about stars moving. like,
And
that
yeah,
fast.
well, and these are moving because the mount is moving the telescope. But you will see how quickly the stars move. Like and in fact, we can, where are we at? So step, okay. So in here, oh, I actually need to kill it. This uses a lot of resources, so I need to kill this. But we're zoomed in here.
How like far out? Like with this.
A long way.
We go beyond our Milky Way.
Oh yeah. Oh yeah. Yeah. No, I can get other galaxies that are way off. In fact, some of the galaxies are these. But you see this? This is staying still. The green lines are staying still, and the software is moving with it. It's because you want to stay on the image, right? So that's how fast those stars are moving. That green is actually staying still technically, at least in our perspective. Oh yeah, absolutely. I'll bring some up. All right, so let me kill this because this is a huge resource waste. So let me kill this.
So is Starlink able to process the internet with all this?
Oh yeah.
Absolutely.
Why is that?
What makes me think like at night when I sleep, I sleep with the windows open.
Mhm.
Just how much the moon moves.
Fast.
I end up having to change my shades because it like it's
Fast.
my face. So
And the moon will fit. Hon, I smell something burning.
something burning.
Is it the fire pit?
I smell it too.
I thought I smelled it myself.
Yeah.
I thought it was hickory smoke or.
It does smell like a fire pit.
I suspect it's the fire pit. Let's just.
Do you pause your class or?
No.
When it's
I don't smell anything in there. Do me a favor, go out to the burn barrel and make sure that that's smoking. Here's a flashlight.
When I was coming up the hill, I almost didn't see it. But I did see it.
Okay. All right, so just close this. We're going to minimize this. I'm going to just stop the guiding because this is part of it. Still calibrating, still figuring things out. So we are going to kill the guiding right here. So I'm just going to turn it off. And I'm going to turn off dithering because this needs guiding also. And down here, I've got a dither too. So, okay, so I've made it so it doesn't need guiding anymore. Okay, so I'm going to restart the script here. All right, and so now this is that autofocus routine. So I'm going to click over to the imaging. And what you'll see here is it's doing a 4-second exposure. Why is that? That's why it couldn't calibrate. Something is snagged. Give me a second here. It's just a never ending. You know, you think you've got it dialed in. I may have picked a spot that was too close to the pier. So let me zoom out here. We're west. Let me let's move to Andromeda. So Andromeda is a galaxy. So let me just move to Andromeda. And we're just going to minimize this, and we're just going to manually do this stuff.
So that's the image it's taken so far.
Yeah, and you can see how everything's blurred, and I can tell that that's because the mount is not moving. It's staying still. So that's how much in 4 seconds those stars move.
Wow.
Yeah.
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 That, it created that blur.
That blur
Yeah.
over 4 seconds. And this is a satellite. This is how far a satellite moved in 4 seconds.
Wow.
Makes you realize how fast we're moving.
Is that our satellites or any satellite?
Some satellite.
ETs.
Okay, so we're just gonna do manual. I'm not gonna. You guys get the idea with the scripting, and that you also see the frustration that goes on with the scripting. So we're just gonna go here to. So we're on the camera right now. The camera's at negative 10.3 degrees, and so everything's looking good. So I'm gonna just click over to imaging. And what the heck is that? That is what happens when the cat steps on the keyboard. Okay, we're just going to do a couple of 4-second exposures. We're going to loop. I'm not going to save these right now, and we're just going to start it exposing. And we're going to see if Andromeda is above the edge of, there it is. You wanted to see another galaxy?
Yes.
That is 3 galaxies. Okay.
So there's the big one, which is Andromeda.
This is Andromeda. This is a galaxy. This is a galaxy. These are in our local cluster. So when they
How
talk,
far are they away from the Milky Way?
well, some people, so we will merge with Andromeda. We will definitely collide. So all of us are gravitationally bound to each other. I forget how many total galaxies are in the local cluster, but I want to say it's like 8. So we're all gravitationally moving around each other. We will merge with Andromeda, and I believe Andromeda is bigger than we are. So Andromeda will win. But like an atom, it's empty space.
In our lifetime?
No, not in millions and millions of years. I don't know. We can look up how long it is. It's not something I remember off the top of my head, but we will absolutely merge. We will go through it and it'll rip the galaxies apart, and they will swirl around each other. And we will probably go from what we are now, a spiral galaxy with that beautiful curve. And this is when galaxies migrate into they're different names for different shapes. And we will become probably just like a big ball of stars. It's kind of early to predict. They've got all sorts of computer models, but it's.
So this might appear a dumb question, but if you've looked out as far as you can, you've never found an end.
Our end is 13.6 billion light years away. It's as far as light has been able to travel since the Big Bang. So you can't see anything beyond that. And the universe, they talk about dark energy and dark matter and so forth. They're totally unrelated. Dark matter, when you hear that term, what's happening is the center of the galaxy is moving things are moving at the wrong rate. Okay. So we can look at Andromeda. All these stars that you see, even the ones here in Andromeda, they're actually in the Milky Way with us. The stars in Andromeda is this fuzz. You can't even distinguish those stars.
There's so many of them.
And there is something really not right. What is going on here? I'm going to end up redoing things because something's,
This is something we just took a picture of, right?
this is live. Each time it moves is a new image. So it'll move here. There you go. There's a move. But something is going wrong. I am probably going to run out to the scope. If the cables have snagged or something like that, it'll do these kind of things. So anyhow, so what we've got here is basically dark matter is there's gravitationally, you've got the closer to the sun you are, the faster. So Mercury goes around the sun really fast and it travels really fast. Pluto goes around the sun really slow. And when you get to Andromeda, the stuff on the outside where Pluto is goes too fast. At the speed it's going, it should be flung off into the rest of the universe. So mathematically, they've had to add, they don't know what dark matter is. No idea what dark matter is, but it's just a placeholder for this extra gravity. And so that's why dark matter is gravitational, because matter has gravity. But really, we don't know. And then there's dark energy. And dark energy is the space is expanding. And this is why, so nothing can travel faster than the speed of light. But those galaxies that are at the edge of what we can see, that 13.6 billion years away, I think is where we're at right now, it's moving away from us faster than the speed of light. Not because it's moving that fast, but the space between us and them, like a rubber band, is stretching. We don't know why the universe is stretching. So dark energy is a placeholder for that stretching factor because it takes energy to stretch things. So they know it takes gravity to hold galaxies together. So that placeholder is dark matter, and the stretching of the universe is dark energy.
So,
We don't
in
know.
the field of astronomy, would you say we're in the Neanderthal stage? We don't know shit.
We know a lot. Every generation or 100 years, whatever, like when Planck got involved with physics, and Planck probably won't mean anything to you. He's a physicist. And this was, I'm sure I'm going to be wrong here, but I want to say that it was in the 1700s. He revolutionized our views of physics. But his teachers went, don't get into physics. We know everything there is to know. We always think we know everything there is to know.
Oh my God.
And we never do. So yes and no to answer that. What is going on here? I am gonna.
Can you see black holes? Have you found a black hole?
You can, yes, we can get images of black. Well, sort of. We can get images of evidence of black holes. So galaxies, every galaxy, essentially, that we know of has a black hole at the center of it.
So would a black hole define be a threshold to a different time?
I don't know what you mean.
Well, I know I'm going way Star Trek on you, but.
I mean, black holes are essentially math gone ballistic. So when physicists are dealing with these math problems and so forth, what happens is Einstein and Hawking and all of these folks were like, wait a second, when matter gets too close together and too compressed, it goes to infinity. And basically, when you have a math problem that goes to infinity, it means it's broken. And that's essentially what a black hole is. Like, black holes are real and it is mass. So most black holes are formed by a supernova. A star that's, I believe the minimum requirement is, how's it going? The minimum requirement for a star to go to a black hole, I want to say it's 4 or 12 times the size of our sun. And what happens is our sun, our sun is the size that it is because at the core you have fusion going on. So you've got hydrogen bonding together. When that hydrogen bonds together, it releases energy. When it releases energy, it pushes out. So our sun is from the core, it's always pushing out. Okay. And what happens is as the sun burns up one fuel, it moves to the next fuel. When it burns to the next fuel, next fuel, next fuel. When it gets to I'm not going to go into the real physics behind it, but they say when it turns to iron. When it makes iron, it's the end of the star's life. And what happens is when iron fuses, it eats energy. It takes energy to do that. So instead of releasing energy, puffing the star out, it stops puffing the star out. And what happens is all that size of the sun or the star collapses in. And it basically, I'm trying to think of the right way to do this, like the whole thing comes in, compresses, and then tremendous release of energy, and it explodes outwards. And what you'll get is you can get a bunch of different things when this happens, but you'll either get a neutron star, you'll get a pulsar or a quasar, and we can talk about these different things, but basically what happens is that's when you get a black hole forming, because the whole thing is collapsed in, it rebounds out, gases expand out, and you're left with a black hole at the center of it. Now, the center of every galaxy is a supermassive black hole. And if you're at a active galactic, excuse me. Sorry. Now, there's active and inactive. If you've got an inactive, it just means the black hole's sitting there. If it's an active galaxy, it means things are falling into that black hole. If things are falling into that black hole, believe it or not, black holes spit out crazy amounts of energy, like terrifying amounts of energy. Because what's happening is you've got this energy well, gravity well, right? You got this incredibly strong source of gravity. So you've got stars potentially being sucked in, and they're literally being pulled out. You'll hear scientists talk about spaghettification, like if you were to fall into a black hole, you get spaghettified and stretched until you're super thin and everything. All these things cause friction. And you've got what's called an accretion disk. And like our sun, our planet was part of the accretion disk that formed around the sun. So you've got the sun is going to form because of gravity, and you've got all this dust swirling around the sun. And because of conservation of momentum, and you've got it always forms this disk, no matter what it is, it forms this disk. And as things move in closer, the stuff that's a little closer is moving faster than the other stuff on the outside. And it causes friction as the particles move against each other. These particles get so hot. We were talking about black body radiation and how you cool the camera for less, photons to be emitted. This stuff is so hot, and it's not emitting regular photons. X-rays are being emitted from this. Tremendous amounts of energy. An X-ray is just a high frequency photon. So at one end of the spectrum, you have photons that we can't see. Then it moves faster and faster and faster to our frequency of light, which you move from red, which is lower energy, to ultraviolet, which is higher energy. And then you move into, I don't remember what you move into, but eventually you get into X-rays being emitted and gamma rays. And, as that energy increases. So these black holes are emitting energy as the stuff moves in. And then what you get is off the sides, you get these jets that stream out. Let me see if I can pull up an image so you can see what I'm talking about.
There's endless discussion on just the black hole.
Yeah, don't get me too deep into this well.
I mean, I just wondered if we could time travel.
You kind of can. So there's a beautiful thing that happens. So again, without going too deep into this, because again, I could spend days at this, but E equals mc squared is the most beautiful math equation and physics equation that's ever existed. And it means so much more. Like people hear E equals mc squared, and it means nuclear weapons and nuclear energy. And it does. That is exactly what it is. You're taking matter and doing things with that matter and releasing little bits of energy. And if you do this enough, like in a nuclear weapon, you get a bomb. You do it controlled, you get nuclear energy. You do it controlled where you're fusing them together, you get fusion, which is happening at the sun, which we're trying to do at the like Fermi Lab. I think Fermi Lab is trying. But anyhow, the point here is that equals M scrum means so much more than that.
I just wanted to let you know, Jackie asked a few questions in the chat.
Oh God, she knows so much more than me about this. Jackie knows her high energy particle physics more than I will ever know my particle physics. What's she asking?
If we switch to manual mode, does that mean the targeting guidance is turned off and that's why the stars are smearing out a little?
No, there's just something going wrong. Yeah, and I'll check it in a second here. But let me just do black hole jet. Helps if I spell it right. There, right there. Those jets coming out here are formed by the matter falling into the black hole. And I apologize. I actually don't know whether it's an electromagnetic or what, but what basically happens is some of the matter that's falling into the black hole ends up moving to the poles and spitting out the ends like a top. So where the black hole spins this way, the jets go 90 degrees to that spin. So it'd be coming out the top of a top and the bottom of the top. And that's what those are. These are literally particles thrown out from the black hole at the center of this galaxy right here.
Blackish, reddish stuff that you see kind of
Up here.
out. No, around the center part. There.
This is the outside of the galaxy. So this is many, many light years from the black hole. So it's not like in school you're taught energy can be converted to matter. Energy is mass. So like I weigh 160 pounds. Out of my were to just take the weight that our most basic particles in matter are quarks. If you were to take all those quarks and take the mass of those quarks, it's going to be a couple of pounds. All of my mass is created by the vibration of my atoms together, is what's actually giving me so much mass. And there's it's the energy of my molecules that gives me the mass. And even those quarks, those couple of pounds of quarks, it's not the quarks. A couple of years ago, they developed proof of the Higgs boson field. Those quarks sit in the Higgs boson field, and it's the energy caused by the Higgs moving around the quarks. So even the mass of the quarks is the energy from moving around it. So it's not that energy and mass move back and forth. Mass is energy. And Einstein also played with, if you start moving fast, matter, although they're playing with perspective, but the old idea, which still for this discussion holds true, that as I give energy to something, its mass goes up. So if I have a steel ball, like this is literally true. If I have a steel ball right in front of me and I measure its mass will be X. I then take that steel ball, I put it on the space shuttle, they bring it up into orbit, and they throw it out the window. It has more mass because it has more energy. All that potential energy to put it up, fighting gravity, bringing it up, it actually has more mass. You can put it on a scale and see that it has more mass. Yeah.
How would you explain the relationship between quarks and neutrinos?
They're different. So they're all fundamental particles. So a quark is a fundamental particle, a neutrino is a fundamental particle. For those that don't know, neutrinos are particles that are basically ghosts. You have hundreds of thousands of them going through your thumb every moment from the sun. Nuclear fusion produces neutrinos, but they don't really interact with matter. So they're just flowing through us continuously in crazy numbers. And they're doing all sorts of, so they've got the ice cube down in Antarctica and stuff. And basically what they're doing is they're playing with, they're playing with neutrinos and light. When neutrinos interact with particles, they produce light. So basically they buried light sensors down in Antarctica, and they do this all, there's a bunch of neutrino detectors. But basically the particle interacts with matter, produces a photon, and we detect the photon. We go, oh, there's a neutrino. And so what they're doing now, when a star goes supernova and it collapses in and it can form a black hole and explodes out, there's a really cool thing that happens. Since neutrinos don't interact with matter, the star comes in, it collapses, boom, starts neutrinos. You don't know yet, though. If you're looking at that star, it takes time for all that matter and energy and photons and everything to move outwards, but the neutrinos are already long gone. And then as those neutrinos and photons move through space, shoot. As they move through space and move through dust and stuff in the galaxy, that light slows down or interacts with things. Neutrinos don't. They just keep sailing through. So neutrinos can detect that a star has gone supernova before, and they tell all the astronomers, look here, and everybody move their telescope there, and then they'll see the star go supernova. It's truly amazing what we've discovered in the last few years. But you've got neutrinos, and then you've got gravitational waves, which do the same thing. But that's with black holes merging and other things along that line. But let me kick back over here and get this going up, because you guys want to see stars. So let me.
You have to go out.
I will, just to make sure everything's good. So I'm going to just send it home. I don't think. Okay, so we're home now. It's just being stubborn on me tonight. Okay, so we're home now. Let's jump back over to the software here. And you could say, so that was it was taking images as the telescope was moving. So here we go. So we'll give it a second here. Boop. And that star right there, that's Polaris, North Star. So let's play with this for a second before I go out and check stuff. Because it's pointing at the North Star, the stars don't move very much. Okay. So what we're going to do here, we're going to see if we can there's some nebulosity around the North Star. It's dark nebulosity, so it's a little hard to see. So what we're going to do here is we are going to jump up our exposures here. So instead of 4-second image, we're going to jump up to a 30-second image. So I'm going to tell it to take a much longer exposure. Actually, first thing we're going to do, we're going to focus it. Let me just jump over to the autofocuser, and I'll explain all of this. So I'm just going to say start autofocus. Okay. So what it's going to do is it's moving the focus back however many steps I've told it. I've told it move it 4 steps. So it's changing the focus in one direction a certain amount, and it's going to do a 4-second exposure right there. It's analyzing this image, and what it's doing is looking at the size of a star, and it's just plotted it. So it's a little over 5. Okay. So now it's changed the autofocus, it's settled, and it's taken another image. And you see that image is gone from 5.06 to 5.035. So the star got a little smaller. What you don't think about when you're looking through a telescope or binoculars, focus is sharp, unfocus is blurry. Blurry is a line spread out. So as you focus it in, those lines get closer and closer and more crisp and more crisp and more crisp until it's focused. So what's happening now is it is looking at the stars, taking a photo, looking at the star, taking a photo. And what it's doing is, as you can see, now it's down below 4.2, below 3.8. So each time it's moving the focus, the star's getting smaller and smaller and smaller and smaller. When it's talking about if you had a telescope up in space, it's a pinpoint. It's almost no size. So what it's going to do here is it's going to keep taking images, and mathematically, it's got a hyperbolic curve at 0.96. Mathematically, a 1 is that perfect curve. 0.98. So each image is what it's expecting it to be in its mathematical curve. Didn't like that so much, 0.96.
So what size lens or aperture is this?
This is 14 inches.
Wow.
And that's another satellite?
Yes, that is a satellite. Thank you, Elon. So
We are happy.
in all joking, okay, like so when you hear the satellite screwing things up, they are, don't get me wrong, okay, but there's two ways it's screwing up. It's really the radio telescopes, okay, they're the problem, because those satellites are emitting all sorts of radio frequencies, and they are screwing things up, don't get me wrong. The imaging, though, the reason the satellite is visible is because sunlight is bouncing off it. So as soon as the sun sets far enough, there's no more light aimed at where the satellites are. The satellites aren't visible anymore. So really, it's in dusk and dawn time frames that I can view satellites. Once you get about an hour after, the satellites you can't see anymore. So for those people that go out and manually look through, it's a disaster for them. For me, who image all night long when I'm sleeping, there's really no impact to me.
Haven't they recently started to paint the Starlink dishes?
It doesn't make any difference. Oh yeah. Yeah. So you can see the curve and the focus. So right now it thinks this spot is its best focus mathematically. And it will keep adjusting this and taking images. Oh, it's done. I'm sorry. It's autofocused. So it's put the image here, and it's got this nice curve. And what it did was, this is mathematically the smallest star, which is in focus. All right, so let's just jump back over to here to imaging. And let's take our 30-second exposure and see what we get. So
we can look at what we're gonna get, and then we can look at the North Star with our eye, and then try to make it correlate.
You can, absolutely.
What really is.
You will.
what we-
So well, wait until this pops up. Hold on. Let's see what we get. And no nebulosity. Okay. That's a shame. Although, what's this?
So it's
Let's.
the second-
It's
I know what that
a
is.
flying saucer.
No,
Yeah, it's ET.
that is likely. Well, no, actually. Okay. Let's figure out what that is. So first thing we can do here is I can say, see, and this is the cool thing. You actually can find stuff that's not found. So let's go ahead and plate solve. So what I'm going to do here is take it's still imaging. I have to tell it to stop imaging. And we're going to plate solve, and we're going to make sure that we're in the right spot. And so what it's going to do, it's taking a 10-second image, and it's going to make sure that it's pointed in the right spot.
Have you ever found anything that was like unexplainable? We found a Cylon once. What is that?
I'm not tracking.
What
is-
I was just saying,
What is going on? Give me a second here. Oh, what? That's my problem. Why did it turn? Whatever. It's all good. I'll figure that out some other day. Okay, so it wasn't tracking. That's what was the problem. It wasn't snagged down there. So the telescope has a gear in it that it automatically, it has tracking rates. So it has different rates. So it's got one rate that follows the stars at their rate. It's got another rate that follows the moon at its rate, and another one that follows the sun at its rate. Okay, for some reason that was off, and there were no gears turning, which is why you saw everything moving. So let's go ahead and give this another try. And I apologize. I've never.
That strange thing, is that something or not?
It's something. I suspect it's a planetary nebula. So let me pop over and show you what a planetary nebula looks like. So I suspect, where did my, oh, that's right, it's here. So I suspect that that is, let's just pop this open and let's do dumbbell nebula because it's one I know. So this is the dumbbell nebula. It's a pretty good image of it. And Wiki is wonderful for finding stuff in the sky. But this is the dumbbell nebula. So you see, you've got basically this was a star that exploded. And this is the shell of gas moving away from that star. So you can get nebula like this two ways. As the star nears the end of its life, it starts sloughing off gas and those shells of gas move further away. Or if you get like a supernova, that explosion pushes gas out. Okay. So let's see, let's have some fun. Let's get some cool images here now. The telescope is showing how much fun it is tonight. So let's have, what do we want to hit? Let's hit, let's go back to Andromeda. So I am just going to, Andromeda is just easy to pick this way. I can just right click here and go to. So there's like 12 different ways I can tell it what I want to point to. This way is just easy and it works. All right, so let's do a crazy image of Andromeda. So Andromeda is very bright. So let's just do a 15-second exposure in Andromeda. And this is a luminosity filter, like I was saying. So this is getting all visible light for, I hit start way too early. It's not there yet.
Do you have like a favorite galaxy to look at?
You said Milky Way. Oh.
Yeah, well, so our galaxy is a great one because of the Milky Way. You've got Triangulum is gorgeous. In fact, let me while it's taking this image, let's do that. Let's back off here. Oh, there we go. Let's do, so what you're seeing is like the bright core here of Andromeda. See, it's just overexposed. There's nothing there. So I can, if you want to image Andromeda well, and this is the artistic side more than the science side, what you end up doing is you end up imaging the core with a very short exposure. So we'll do, let's just do a 5-second exposure. So we'll do a quick 5-second exposure of Andromeda. And let's just pull up, while it's doing that, let's just pull up some facts on Andromeda just so you get an idea what you're looking at. And I'm going to spell it wrong. Oh, I don't have to spell it wrong. Okay. So what I'm looking for is distance.
Well, your picture looks as good as that one right there.
Oh, it's showing some stuff here. So I don't see. So we're going to collide in around 4 to 5 billion years with Andromeda. But distance. It's got 1 trillion solar masses. So Andromeda is the size of 1 trillion of our suns. 2.5 million light years. So the photons that I'm collecting left Andromeda 2.5 million years ago.
It could not even be the same image.
It's not. We're looking at stuff that doesn't. We're imaging stars that went supernova already. They're not there anymore. So I'm looking back in time. So let's click back over to our Andromeda here. So smaller, you see the core is a little bit better. And then let's go crazy. Let's just absolutely have fun. Oh, well, that was 100 seconds is fine. I know, I know how to party. I definitely know how to party. Shush. Whoa. Oh, apparently I need to put on my glasses. That's 1,000 seconds. We are not waiting 1,000 seconds. Well, let's just do 60. I look down and I'm like, 16 minutes. Okay, so 1 minute, we'll get that going. All right, now let's, what's the next thing we want to image here? Let's see what's in the sky. All right, so, do I have, so I've got solar system, I've got constellation. Yeah, NGC objects. Okay, so we got everything there. So I happen to know that I suspect that. M39 doesn't seem right to me. So, and this is where the fun begins.
So Tom, did you pre-map all this? Or is this part of the software?
This is the software.
Okay.
So this software is made by the company that makes the mount to control the mount, Celestron. So I think let's see what M39 is. M39. So these are all like this is M is Messer for. I didn't mean to do that. M39. So basically, these guys developed M39. Messer 39. So no, this is just a star cluster. We don't want to do this.
I think I like the color filters. I know you have to do that all night, huh?
So the image that I'm going to bring up, I'll show you guys how to combine it, is 12 hours of images. So, okay, so we're on Andromeda now. That's probably done imaging. Let's pop this up. Hope it's 44. This actually might be it. So look how big out this goes. So Andromeda, what you think is just this little thing, goes way, way out. It is bigger than I can image in one image if I go out to the edges of it. It's incredibly big. I want to say it's like 4 or 5 times the size of the moon if you stretch moons across. For some reason, my gut actually says it's bigger than that. But tremendously big objects. And you can see this isn't gas and dust. These are stars. This fuzz, this color, these are stars. They're just so far away you can't identify them. All of these stars are in the Milky Way with us. All right, so let's jump over to the sequencer here. And let me jump to, actually, let's jump to our framing wizard. And let's just grab something here. Just go here, and I'm going to, sorry, I got to stop. When it's imaging, it's kind of a safety protection that it says, don't allow me to do anything. So we're going to stop that image. We're going to go back over here to our framing. And I'm going to say slew and center. So what's happening right now is the telescope is moving to, the software has just told the mount, I want you to move to this spot. It's going to move there, take an image, compare it against what it knows, and then make an adjustment or two to get it so it's exactly where I've told it that center to be. So right now we're still slewing. It's settling, so it's there. I can see down here, it's in the mount, it says settling. So it's just getting back into the tracking again. So now it's exposing for 5 seconds. It's taking that image. There's the image, and now it's plate solving. It's comparing it against known stars. So we're going to click back over. Scope not inside tolerance, so it realizes that where it's told to go is not quite right, and it's giving it another adjustment, saying move this way by this amount. So we're going to go back over here to our imaging. Here we go. Let me zoom out because that doesn't mean much. And what you've got here is it's darker in the corners because I don't have those calibration frames. When you apply the calibration frames, it makes the whole thing even across. And I can do that in software too. But you can start to see stuff going on right here, right? So it is now, so the first image, this is what's telling me. It's telling me the error was 1136 and now it's just 14. So it's it's way less than a second accurate. So now let's go ahead and do that 60-second exposure. So let's get our guiding back on because it's a long exposure.
How long did it take you to learn the software?
I don't even know this software yet.
He told me years. I asked him earlier so that we didn't feel
I
so.
mean, this is astronomy on a whole different level.
I
It's
know.
like,
Yeah. Okay, so we're going to guide on this. We're going to see what happens here. So I'm watching this. Let's clear this. Let's see how bad this goes. So this is okay. We're still okay. We're still, oh, it's coming back in. We're still okay. Okay. All right. We're good. We're good. No, a little less. Stop. Go the other way. Go the other way. Okay. So you can see all of these are on an axis. We're going the wrong way. All right, stop for a second. Let me just, because now that I know what the problem was, let's go ahead and delete our calibration real quick. Get our imaging going. It'll automatically calibrate here as soon as I start it. So now the calibration should work. Okay, there we go. So it's starting to, it's telling the scope to move. It's remembering where it's moving, what the direction is, what's going on. It's learning. So we're gonna, while that's doing that, we're gonna just click back over to here. Oh, there's the satellite. So you can start seeing that nebulosity. This is the elephant trunk nebula because these look like an elephant trunk. We're not real creative when we come to naming nebulas, honestly. It really doesn't look like an elephant trunk to me.
I can't see it.
Yeah, it's not. Oh, and this is caused because it's calibrating the guiding. Once you start going beyond like 30-second exposures, you need the guiding. It really needs to be there. So we're just doing this. Let's kick back over to our.
the software feels really dangerous in the sense that I would just be totally consumed and
Yeah.
not be able to get away from it. Like,
Oh, it's
you talk about exploration. You just go.
oh,
and
it's.
go and go.
It's really amazing. And well, and one of the things I'm not there yet because I'm so with this telescope, with these, okay, so real quick, the skies that we've got, let me show you why we picked this spot. We live here because of this. This is a satellite looking down, and this is the light pollution. So you can see the darker it is, the less light pollution. Guess where we live?
In the dark.
It is the skies in the United States that are on our road.
What is Gallup?
Where actually is Gallup? Oh, there it is. So Gallup, in the city of Gallup, yeah, so their Bortle is so it's their classes, and they go up to class 8. We're in class 1. It doesn't get any darker. This is as dark as the skies get. So when you go outside, if you went here to this darker area, there is a Bortle class 1. But I can already tell you, you can't buy property there. About the only places that are class 1 are basically national parks and things like that. So, and I was a little like, there are places that you can get, but it's rare. But anyhow, so that's what I was doing funky things. So anyhow, yeah, we're right here in, give or take, we're class 1. We've got very little artificial brightness. So this is literally why we bought this house. My old telescope, the ones that when you see old images that I put up, there's Nashville, there's Chattanooga. We were right here. East Valley Road. Class 4. So the more light pollution, what it does is it just causes like a glow to the sky. So you got to totally change it. Shorter exposures, more filters, things like that. I can image anytime. Like, and the weather all winter long being as clear as the skies are here, I can image every night. In Chattanooga, I was lucky if I got one night a month to image. So it's truly amazing here. Let's go back here. Okay, good. Guiding is done. Let's clear here and let's see how we're looking. So it takes it a second to settle down and get back into its groove. Okay, yep. See how it's pulling in? It's making little teeny tiny adjustments here. See how big these adjustments are because it was way off? These are just little teeny tiny adjustments. It's still a little off, but it'll pull it back in here. So I think we're good with the guiding. I think that problem was just that the scope was turned off. So let's go ahead here. Is it doing it again? Oh, I'm sorry. This was a minute exposure, so it was still doing its thing. Let's go ahead and stop that. Let's let this settle in. Just clear this. Clear this. Okay, pulling it in. It's still off a little bit, but this is within reason. I think we're going to be good here. So let's go ahead and do a 30-second exposure and just kind of see what we get here. Oh, and while it's doing that, what I can do, I took all these calibration images, and what it does is, so under Veil Nebula here, these are what they call lights. They're the actual images. So you can see that in this, thought the cat was throwing up a fur ball.
This is more a streaming question, but can you pause if we were like to gather up and just?
No, I can't.
Okay.
Unfortunately, I mean, if people need to go, absolutely, take off, and I can take a quick break. But what I've got here is 1,083 images, 123 gigs of images taken over 4 nights. So I imaged one night with the clear filter, one that collects just hydrogen gas, one with just oxygen, one with just sulfur, and that's what these images are. So this is all of those images put together into each of those individuals. So I can now take these from this morning. So this software is like Adobe Photoshop equivalent for astronomy. So I can then window, tile, to lay them all out. And you don't see anything yet, right? So each of these images is different. This one right here is the luminance. So this is all visible light. This one over here to the right is sulfur gases out there. A star is emitting ultraviolet radiation in the other called lights. And the sulfur gas state doesn't want to be up there, drops back down. Quantum physics says it's a specific frequency. everything emits different than this one up here. This is HA, which is hydrogen alpha. So that has received that energy and dropped down, emits at a specific wavelength. That filter allows just that wavelength of light to go through. And then over here, excuse me, this is oxygen. So now I've got these images set up, no problem. And what I can do is just real quickly, while my vision is coming back.
The filter is measuring this, the software through the photon wavelength.
It's an actual, so it's a black and white camera. So any photon that it receives through the frequency of light, because it's all it allows through.
They're different, but they're similar.
They're very similar, but they are different. I mean, you can, by the way, I'm going to turn this upside down because all I see here drives me freaking nuts. Yeah. I expect it to open with the thing to come out. I hate this image like this. So let me zoom out a little here, you know. Yeah, no, it's creepy. Don't get me wrong, it is creepy. So what I'm going to do real quick here is let me under scripts here. Oops, sorry, processing. What I'm going to do is see how the edges are dark and the middle is kind of that gray. What I can do is I can even that out. If I don't even it out, when you combine them and say this is red, this is blue, this is green, you get mush. So
Do you flatten them?
Essentially, yes.
Okay.
It's different terminology, right? It's it's the same technical, but they use different terms. So what I'm doing here, so the first thing I'm doing is gradient correction. And this will appear on the wrong screen. All right, so I'm going to just drag this over here. Okay, so this is gradient correction. So this will correct that fuzziness. So we'll start over here real quick and drag it down. Pops open, does its magic. And by the way, this software is brand new to me. I am going to be spending a very long time, very, very long time learning the software. I know not even the most basic of it yet. So I'm going to do it again just to get this evened out here. Okay, see it's evened it out a little bit more. I'm going to do another one. With astrophotography, you do little steps. You can do everything in one shot, but you just overshoot every time and then you kind of start over. We're almost there. I've got a little bit here that I want to get rid of. So I'm just going to tell it to run it again. And anybody that knows this software, if they watch the stream, are going to be like, what the hell is that guy doing? He's doing it all freaking wrong.
This may be another elementary question.
Mhm.
You mentioned it. What's the difference between physics and quantum physics?
Okay, so they're both, physics is overall.
Yeah.
Quantum physics is when things get really small. So have you ever heard of quanta? Yeah, I want to quantize something. And so basically what I believe Planck came up with was that energy is in packets is kind of how they say it. I don't love that, but that's the term that they use. It's a defined amount of energy and you can't divide that. So an electron moving down an energy state, that energy has to go somewhere, right? I mean, conservation of energy. You can't create energy, you can't get rid of energy. So by that electron dropping down to a lower electron shell, that energy has to go somewhere. That energy is a photon. So a hydrogen atom dropping down always emits that amount because that's all it can emit. Because it's a packet. It is a specific size and you cannot divide it any further.
And that's a quantum.
Quanta. It's a quanta of energy, not quantum, quanta. Excuse me.
So quantum would be a bunch of packages?
Quantum is like quantum leap. I think it's related, but it's just a term. So
I just read.
So quantum physics is dealing with quanta, and you're talking about physics that doesn't make sense to you and I. And it's all so you can take a photon with a decent amount of energy. So let's say ultraviolet. because ultraviolet has more energy than infrared. And you can take this photon and you can throw it at a crystal. That crystal will absorb that energy. The electron moves up to a higher energy level. Now, certain crystals, when that drops down, because you can't create and destroy energy, and it's got to be the same amount, it emits 2 photons instead of 1. But the 2 photons added together have the same amount of energy as that original photon that came in. Because you, again, energy in, energy out, it all has to match up. But there's this beautiful thing that happens with those photons. They're entangled. And this is quantum mechanics. So you've got, and the beautiful thing is those photons, because of conservation of energy, if one spins one way, the other spins the opposite way, because it has to maintain balance. It always maintains balance. Beautiful thing here, though. I can take those 2 photons and they spin both directions. This is the part that doesn't make sense to us. Like in common, what it is it's a waveform. So both of them are doing the exact opposite wave together, and they're both doing it at the same time. But as soon as I look at one, it's right here. This other one stops too, at exactly that spot. It's bizarre stuff, but it's incredible. Because of conservation of energy and momentum, they have to stop at the same spot. And you've got physics that shows, and it took me a long time to understand this physics. I for months was watching YouTube videos trying to understand. Einstein had this problem with this. So some physicists were like, it's both at the same time. And Einstein's like, that just doesn't make any sense. He's like, one's spinning right when it's spinning left, until you're saying until you look at it, it's doing both. He's like, no. What's really happening is you have a pair of gloves. One's right, one's left. You're putting one of them in a suitcase or a briefcase, and you're giving it to somebody, and they're going to the North Pole. Just because they don't know what glove is in there doesn't mean that the glove hasn't already decided that it's a right-hand glove. And when you open it, it doesn't change. It's still a right-hand glove. And then the other one is obviously going to be a left-hand glove. So they did this experiment. And what happened is that they sent these entangled particles 2 different directions, and they analyzed them. They looked at them. And what happened is that they looked at when they matched in a certain way. And basically it was one of 3 possibilities. And when they analyzed one, the other, so they're sending groups of them really down. And basically what happened is they're looking for when they're both essentially the same. And what happens is mathematically, if they've already been predetermined, so right, if they're opposite of each other and you're just randomly taking them out and they're random because it's A or B, you get 50%, right? 50% one, 50% the other. When they did this math, though, because it was 3, they were looking for this diagonal line, truth tables from school where you lay out all the heads, tails sort of thing. What they did was there was a diagonal running through where they were both heads and both tails and so forth. And what it should have been mathematically was I believe it was like one third. So if it's predetermined because of this, the answer is 1/3. If quantum mechanics is true, because they're heads or tails and it's random like this, they're 50%. And every time they run it, it's 50%. It cannot be predetermined. It has to be this. And it took me months of watching YouTube videos to finally have it click in my head what the experiment was that they actually did and how it came out. It's amazing stuff. And it proved 100% that it is not determined until you look at it.
Did you say it's consciousness and intention playing influence on the particle? Right?
No, because what they did
That's what I
was
was getting at.
they then said, okay, all right.
I mean, I can go way out there.
Oh, yeah.
and
No.
be conscious
So-
if you want.
So what they did was they said, okay, maybe we're influencing this, right? Maybe it's us. Maybe it's the way we're creating these that we're then measuring. They pointed a telescope at a galaxy and grabbed photons that had been created many, many millions of years ago. So we could not in any way influence the photons. And the exact same thing happened.
But if everything's entangled,
Everything is not entangled. You have to create the entangled. So
so if quantum physics is saying we have entanglement,
you can create it. Yep.
but it doesn't exist in nature.
No, it does.
They create it.
No. It does exist in, but
How are we not entangled with?
entangled photons and entangled things are created by the way that energy is created. So you have to have the two of them created at the same moment. So two photons created at the same moment. So you've got that energy coming in, one photon coming in, hitting a crystal, creating two photons. Those two photons are entangled. I can now take each of those photons and do something with them, send them somewhere. But this is where some of the insane cryptography is coming in, because if I can create these two photons, one of the things that's entangled is its not polarity. It's what are the sunglasses that you use when you're fishing? Polarization. The polarization is also entangled. So I can send them through a polarized filter. Each one I give to a friend and one I keep. And I hit a polarized filter and say, this is polarized right. Theirs is going to be polarized left, but that doesn't matter. We just match it up. So I polarize one way, A, and they polarize, it's actually B, but we'll call it A. So they're both the same. They're actually exact opposite, but let's just say that they're the same. That's our counting. They're both one. Here's the beauty of it. Now I can exchange data and I can be like, I got one, but I'm not going to tell you what it is. But I know what yours is because our photons were entangled. So I can send them each way. I get a 1. I know they got a 1. So I can be like, I got one. Did you get one? Yeah, I got one. I know he's got a 1. Next one comes through. I got one. Happens to be a 0. I know that theirs is a 0 too. You see, I can build up numbers, right? So I get enough of these and we have numbers that nobody else knows. Here's the beauty of this. If somebody else were to intercept in the middle and get that photon, they cannot know what it is before they send it off. So they can't be like, ooh, we got a 1 and then send a 1 down. Because as soon as they know it's a 1, it's destroyed. It's gone. So you can't know ahead of time what you're sending down to somebody. So there's no way for somebody to get in the middle, intercept it, and resend another one down. It is a encryption, or it's a hack-proof encryption. No one can intercept it. No one can be listening on the line and get it, because as soon as they receive the photon, it's destroyed, and they cannot recreate the same one and send it out. Now, they could do the same thing to create a pair and send them down, but you don't know what it is until you measure it on the other side, and they've just received it, and you've just told them like it doesn't work anymore.
So how does entropy play between that entanglement?
I don't think it really does. So entropy, for those that don't know, is the idea that if I have a glass, everything goes to a disorganized state. So it goes from organized, as in liquid in this bottle, and I drop it and it shatters and it goes across the floor. The entropy is increased. Oh crap. It's gone one. I guess it's entropy is, I can't remember which way it goes now.
The vacuum of the positive.
Well, so entropy is the idea that like this water in this cup is organized. It doesn't want to be organized. It wants me to pour it out on the ground and spill out all over the place. We're getting into there are some crazy physics stuff because you can't reorganize and everything. But let me get back to this. All right, so we've corrected the gradient here. Let me correct the gradient in these two real quick. And what we're gonna do is we're gonna make a color image out of these.
That's when you get them all shaded out and then over.
Can you take a break so that, I'm tired now,
Yeah.
we can go.
Yeah,
So, thank you so much. for
Of
having
course.
us over and entertaining our questions.
You get the stuff together while he's doing this, I want to see the colors.
Yeah.
Lighting everything up.
Okay. Right.
it's fairly quick. So what I've done is you can see these other ones are kind of more equal on their gray. So I'm just going to keep going. We've got some dark in this corner here. Okay, that's pretty good. This is close enough to figure out what's going on. Now, the problem is when I went from dark to light, I didn't actually change the image at all. These images are still basically black. So let me just shrink this down. Okay, so let me just put these back in their natural state. Give me a second.
Oh, it's over there.
Oh, it's F11. Why are they not? Okay, well, I didn't stretch them. So okay, well, whatever. So we're gonna go ahead and combine these now. So let's go ahead and again, it moves over here. So let me just drag this over. So this is basically saying what image is what do you want? Okay, so what I'm doing here is I'm selecting and saying for L, for luminance, how bright it is, I'm going to choose the luminance image. And for red, I really like, and I can choose whatever I want here. Like I can choose to have anything be any color. So I'm going to choose the red, the hydrogen alpha to be red. And I'm going to choose the oxygen to be green. And sulfur is going to be blue, which it already is here. So there's our sulfur. All right. And now, yeah, I've got luminance drop down. And let's see what we get.
So this might seem like a really like question, but going back to like the photon thing and like
Mhm.
how like the entanglement and everything, and how you said that they changed based off the fact that like we observed them, and then how we had when we looked back at like a different galaxy, and they still changed, right? And it was like,
Yes.
how can we not know that, or how come they changed even though it's like technically back in time?
Well,
So,
yeah, they were afraid that somehow by us generating the photons, we were interfering with things. So the idea was that they were yeah, exactly. They were, if it's already been created light years ago or hundreds of years ago, thousands of years ago, millions of years ago, we obviously could not have interfered with the creation of that energy.
So I wonder though, like from a human perspective, obviously time is linear,
Mhm.
but what's to say like it still wouldn't react to us observing it? Like,
Well, it does.
considering-
That's the beauty of it. By us observing it, it does react.
Considering like if time wasn't linear, then it would make sense. Like, you know, it would react no matter what to us observing it.
Yes, and that is the goal. And realize you're at the edge of my knowledge of it. So you've also got two knowledges of like what I know and what I can explain.
Yeah.
And so you're beyond what I can explain, and you're right at the edge of what I know.
No, I feel that. I feel like honestly, if we could like figure stuff like that out, it would explain stuff like I don't know, just would completely open a whole other door of this.
Mm-hmm.
It's just fun to get creative with this.
It's amazing. Let me see if this will let me. Yeah, okay. I'm gonna just change this stretch real quick.
Also, based off of what you know, do you believe in time travel? Like,
Yes. Okay. So there's a beautiful physics thing that happens. As you increase gravity, you slow down time. What's the biggest gravity you can? Mhm. So what happens if you were to fall into a black hole looking out at the universe?
I've heard about this. Isn't it like you can see time as like
End of the universe in front of your eyes. So let me.
Engaged in this conversation, but my brain is fried.
No, I always thought that was like interesting. Also, like, have you ever seen Interstellar?
Yes.
So, what do you think about that movie?
It's fantastic.
I'm just gonna lay it down.
I liked how they like made time like a physical thing. You know, 'cause-
The end of it went bizarre, but the main part of it, like their physics was amazing. The image of the black hole is exact. The only thing wrong in Interstellar with the image of the black hole was that the side moving towards you with the black hole spin would be, and you basically he went the wrong way. He went to the I believe the bright side for cinematic effect, and really you would go to the dark side because that's the direction that would be easier for you to move towards, because it's moving away from you, so the light is going to have less energy and it's going to be darker and it's going to be more red shifted. The side that's bright coming towards you is not the direction you're going to want to go. It was something along that line. That was really the physics problem with it. But just to let you guys see, it's going to take too long to bring this up. This image is that. So the red, yeah, the red here is hydrogen gas. The blue-green is oxygen. So you can actually see what gases are made up in the nebula. Of course. I'm going to end up, you know what? I'm going to kill for, you know what? I'll keep the live stream going. I'll continue playing and I can actually interact with folks on there.
Okay.
Thank
you so much.
Oh, thanks, Jackie. Yeah. I half it. I get lucky. All right, guys on the live stream, I'll be right back. They're gonna take off. So, but what we'll do is, I'll show you some stacking and we'll get some nebulosity and stuff going. And for those on the stream and for folks here, what I'll do is, I'll get I'm going to be posting stuff on Astrobin when I get it, and I'll basically share out the link so everybody gets to see these images. This telescope produces stuff that is just, well, incredible. So give me just a minute and I'll be right back. And she throws things at me.
Thank you, Tom, very much. But what I wanted to get to was that there's a new article on quantum physics and the consciousness of our mind. When we die, our consciousness, it still exists as we know it.
You don't want to know.
Well, I'm telling you, I think it could be okay, but if you say, no, I don't want to know your taste, I absolutely love the beauty of that.
I hear you.
I do love it.
I didn't get to introduce myself.
I was there.
I was
Sorry.
Chrissy, nice to meet you.
I feel like, you have to read the presentation, almost like, are you a professor or?
No.
You'd definitely be a teacher.
This is all just,
And to meet my niece.
Well, nice to
I
meet
mean, I'm a Shauna.
you. Nice to meet you.
Yeah, that was very impressive.
On your all these cars at the time, okay?
Oh, by all means, yeah, stop.
Because that's what,
Just stop running in.
because that,
That's what it is.
yeah. And here's the thing, this, like I said, so this software that I'm using is still developers.
Yes.
That's how fresh I am with this. The software that I was using, they really haven't updated it. Everybody's moving to this. And it's like, so far, all I've done is analysis. So
You're amazing.
Yeah.
No,
As a scientist, if you guys want to, like, I know everybody's like, if you want to take 30 seconds and run down and see the scope,
Yeah, let's
I'll show you that.
love to.
Oh, hold on a
Thank you
second.
for coming.
You guys now. You got it? It was fun. Before you leave, anything you want to take with you?
Oh, no, I got food at the Wazoo.
Oh, thanks, Brenda. No, it's so good to see you
Yeah,
guys.
and we're moving in this weekend.
Oh, hell yeah.
So I've got my movie truck at the house.
Moving truck.
Moving.
Moving. I was just
It's
like,
not moving truck.
a mobile cinema.
Yeah, yeah. No, we are. So here's where I turn.
No.
So black hole eventually went that rate through quantum mechanics. Basically, our entire, I mean, so far I've had our experience, but our entire world is this wave of energy. Okay, and I can't even say that there are virtual particles. Okay, as it is high energy, these particles can pop out of existence, help you with quantum concentration of energy. Has to be two of them, and they can be exactly the third type.
To get out of school gets a little harder, so instead of well, I focused a lot on piano in college, and actually I started composing electronically when I was in high school, so that's really when my focus went. Was electronics production. No. Difference between No, these are horrible. These are just
I'm imaging every night, so. Of course, anytime. Yay.
Yeah,
Hey, Muffin.
okay.
It goes good.
Let's know if there's one person left in the chat.
Okay. Yeah, I'm not surprised.
If they're still there or close it up, I don't know.
No, we got 5.
Oh, you do?
Yeah.
Oh, Lo Santo.
Ooh.
Sorry.
All right. Are you guys still with me? It looks like I still got 4 or 5 people in the room. You guys still there? I mean, I can't tell much from here. It looks like there's 3 people. So now people dropping off. So let's get some imaging going on here. Either way, let me get this. Okay, so we got some nebulosity. Let's go back to our sequencer here, and let's stop. We got to stop the imaging. So let's kick off the manual imaging, and let's jump over to the sequencer, and let's go ahead and start this back up and see what happens. So it's going to this meridian flip. So basically it's moving the telescopes from one side of the pier to the other. All right, so here it goes. Hon, you were doing some music?
What was that?
Yeah, Jackie said you were entertaining with music.
Oh, weird.
Oh, I got a little. Oh, that's my mouse. I'm like, there's something on my screen. It's just my mouse. My vision sucks. Mm.
Oh, so exciting.
All right.
Oh, that was Jeff?
Hmm?
That was Jeff?
Jackie.
No, your coworker. You had someone that was from work on it.
Oh, I sent it to a whole bunch. I have no idea who was on. I didn't actually see.
Yeah, let me double check.
Oh. Oh, gotcha, Josh.
Avenging Souls.
What game? Like what? Avenging Souls. Like what?
I don't know, I've never heard of
Yeah,
it.
what-
It
what-
might be a really cool name.
What game you playing, Josh? All right. Looks like we're flipped. Let's jump back over to the software here. All right. So what's happening now is, so it did the flip. Now it's kicking into autofocus, and it'll do that beautiful graph, the hyperbolic graph, which is far better than a human can focus. Like, I can't come close to the focus that this thing does. Okay, that's a freaky angle from the camera. I'm leaving it. So as the night goes on, as the night goes on and the temperature outside changes and the temperature of the scope, the focus actually changes. So you can't just focus a telescope and be good all night long, which is why this continues to focus. The problem earlier was that somehow, and I don't know how because it's never happened before, basically the scope automatically knows that it needs to travel across the sky at a certain rate. So the scope is set up and it's on a star and it just moves. And it's kind of like a default rate, like it's almost like a cruise control. And what happened is somehow that got turned off. So that when we were pointing it at a spot in the sky, it was not continuing to move. It was just sitting at that fixed spot and the stars were moving past the scope. I've never had that happen before. And of course, it happens now. Murphy's Law. So look at that hyperbolic curve. We are at 99. It doesn't get any better than that. That is as perfect as you can get. And now it drops down to 96. So actually I can just work on this screen basically. So yeah, so the scope just dropped tracking. As soon as I turned it on, it went. Sorry, rubbing my eyes. So the autofocus is almost done here. That's a really nice curve. That is a beautiful autofocus. And those are very small stars. It's three. I can't remember if it's pixels or arcs. I believe it's pixels. Oh, that is nice. So it's taking an image, and you saw down in the corner there, it's plate solving. So it's making sure it's pointed in the right direction. Scope not inside tolerance. So I can't, when it does this with this image up on the screen with the meridian flip procedure here, I can't change the screen. It locks me out right now. So I mean, I could cancel it, but we just have to hang tight while it's taking an image. Knew it wasn't pointed in the right direction, figured out how far off it was. It's retold it to point that direction. So we're taking another image now, plate solving. And the beauty of this is this will go completely automated. Beginning of the night, I can turn it on, and I wake up in the morning, and it's done. And I've got gigs and gigs of images to go. It's run through that script. And I have had successful nights where it's done that. In fact, just the other night I had one, but I forget what it was. What screwed me up? Oh, the calibration of the guider. I need to do some research on that and figure out why it's trying to calibrate the auto guiding facing the North Pole. So I need to go and do some research and figure out why in the world it did that. That it's weird. But again, I keep every night basically I'm adding an additional piece of functionality, or it does, I add the functionality and expect it to do one thing and it does something completely different. Like right now, it's going to refocus now. And the reason it's going to refocus is that mirror at the back of the telescope it can wiggle, it can move. So when it goes from pointed up to down and around and back up from the other side, that mirror can shift, which can change your focus, which is why it needs to rerun the autofocus. But if it had the meridian shift, why did it do the autofocus, then meridian shift, and now it has to autofocus again? So I'm definitely still learning about all this stuff. Oh, that's an interesting. Yeah, so far that's a pretty bad hyperbolic. Hopefully it gets better here. So it's a difficult hobby. What is that? I mean, they're still small stars, but that is a very unusual curve. I wouldn't be surprised. Yeah, it's going to fail. See, this is the kind of stuff that I'm dealing with. That is the wrong pair of glasses. What is going on there? That ain't right. Let's take a look at our imaging, see if there's something obviously wrong. They're moving. What's going on here? So that looks okay. I think the scope hadn't settled when it was trying to autofocus. Something was going on, but it failed the autofocus and it's restored it to the original position because it's going to be close. And now it's trying to plate solve and figure everything out where it is. So we'll see how well it recovers here. So it's slewing, it's moving to a new spot, getting everything focused in, or I'm sorry, aimed in the right spot. Why is it still slewing? It's not. Looks fine. What's going on here? This is strange. May have been the auto guider there causing a. Just gonna stop it here. I'm wondering if I need to reboot stuff. Let's forget here. Okay, so that's good. So it moved for me. So it's somewhat behaving itself. Okay, so now it's solving. Let's see if that kicks it in. Okay, so it says it's reslewing. So mount, so for some reason it didn't realize that the mount had gone where it was. So it looks like it's back in the right spot again. Let's see if it solves it properly this time. So it's exposing. There's our image. Solving. Telescope not inside, so it recognizes that I had moved it. It's not in the right spot. So now it's telling the mount like where it really is. Now it's reslewing to the correct spot. There we go. Okay, so it's settling the mount. It knows that it's gone there. So whatever it was, it glitched there for a second, and the scope went to where it told it, but it never said, "Hey, I'm there." So again, we're exposing another image here. Plate solving. Looking at the stars. Okay, so see our error has gone from fairly high to pretty small. And that was close enough. It's happy. So it's actually doing a real full image here. And this will be of the Veil Nebula. And this is luminosity. So this image is going to be way overexposed at a minute. So while it's taking this image, I'm just going to jump into the sequencer here. And instead of it being a minute exposure, where are we? NGC. So here we go. This is the, so I'm going to go ahead and turn these functionality back on. And turn back on the auto guider. Turn back on the dithering. Turn back on the dithering here. And what I'm going to do here is change this from minute exposures, because this is such a bright filter. It's going to be overexposed here, and I can actually show you that. Oops, not what I wanted to click. So in imaging, so here's the image, and you can see the nebulosity up here, and you can see it down here too. The problem is that because it gets all light, the stars are so bright, it like overpowers it. So what I can do here though is click on statistics, and what it's telling me is it's the maximum brightness of a pixel is 65,535, and you've got 34,820 of them that are overexposed. So there's this image is way too bright. So what I need to do is just jump down here to my sequencer and say, hey, instead of doing a 60-second exposure, do a 10-second exposure. And there we go. And so we can jump back to our imaging. And I'm just going to stop and restart it. Stop, start. So it's going to get the guiding turned on, and then we're going to slew again. No, it's gonna want to calibrate again. So I'm gonna kill it. I'm gonna stop it and I'm gonna jump into here. It's funny, the auto guiding has worked so well, and then tonight suddenly just nightmare. Guider. I'm just gonna fully kill the auto guider. It's done. So now that everything's moving right, at least we should get a good autofocus, which we didn't get last time. There is actually some software, their recommendations for the exposure. I have not had good luck with it. The best thing that I have found is that method of looking at the statistics of the image and just seeing how much overexposed it is right here. So how many spots are maximum exposure? And see, we're down to 1,000. So this is still overexposed. Not by much. Most folks seem to want something around 500. And I've had good luck with that. And in fact, while it's doing this, I'm going to pop open, go back to the software here. I couldn't finish this before. So let me take a look here and see if we can image. Turn off the screen transfer. Why is this? What's weird is these are not, I feel like they've been saved or something. These are not letting me unstretch them. Let's try this again. Let's kill all of these. It's just super easy to reopen them. Yes, I want to close the windows. Close the windows. Close the windows. All right, let's just real quick start over from scratch, drop them in. Okay, here's our images. Let's tile the windows so we can see our 4 different images here. And I am just going to stretch them right away. And okay, so it did close. Where's our stretch? It's too big of a list. God, my eyes suck. Sorry, I actually need to, I just can't read this. Where's my stretch? Please. Screen transfer function, there it is. Process all processes. Come on. Screen transfer function. It's not really the one I wanted. I'll bring it over, but It's not auto histogram. It's just too small. Histogram transformation. That's the one I wanted. Sorry about that. All right. So we're going to go to histogram transformation. All right. This is what I was looking for. All right. So let's do this one first. Bring up a preview. And what we're going to do is we're just going to make this brighter. We're going to clean up this image. So we're going to go and tell it I want to do, which one is selected? We're going to do HA. So HA, just to make sure, I'm going to reopen this. Okay, so we're on HA and I'm going to open up my preview. So again, we want to take little chunks. So we're going to go ahead and apply. That's going to be too much. So we're going to bust this down a little bit more. Again, we're going to do it in chunks. So we're going to apply. Oh, it's too much. Well, no, that's good. I'm okay with this. I wouldn't take it the next step to this one. So let's move to this image. And what I want to do is I want to make them all pretty much as close to equal as I want. When I did the stretch before, when I combined the colors, it was all green because the green shade was too bright. So let's go ahead and bring this up again. That looks good. Let's go ahead and stretch it. Stretch it again. Stretch it again. And this is the luminosity. That's why you see these stars like this. Oh, too much. Well, this is actually okay right here. So we're not going to do another one because obviously that would blow it way out. All right, so we got two of them. Let's go down to this guy right here. And we are going to choose, which one is this? And there's our sulfur. And let's pop that open. Okay, there we go. So let's go ahead and apply it. Keep going. Keep going. Let's do one more. That looks good to me. So you got some sulfur here. That looks good. All right, let's just do our oxygen. And there's our oxygen. And let's go ahead and pop over the preview. 1, 2, 3. All right, that looks good. But you see how gray this is. If I use this as it is right now, it will wash it out. So I don't want to make it any brighter, but what I need to do is I need to make it blacker. So probably right about there. I like that. Let's go ahead and apply that to it. So there we go. So the image is dark. And you can see, I mean, I need to balance this better, like if I was making a full-on image. But that's not bad. I got no issue with this. So let's real quick do our gradient correction just to level everything out. There we go. And maybe one more. Okay, that looks good to me. Although I want to make this one a little darker. So let's go back into our histogram. And we're going to be choosing this guy. And we're going to go to luminance. There's our luminance, and I'm just gonna darken it, the blacks just a little bit. Oops, and I need to do a preview. All right, so let's go back to this. So this is the original. Let's go a little bit more black. Oops. Okay, that should be good. We've got some nebulosity here. It's not great, but it's luminance. It's not, I could do this image without luminance. And go ahead and let's minimize this. Let's kill this. Okay, so now we got our images here. This one's still a little bit gray. This should be darker, but let's see what we get here. So if I do process, all processes, and it's LRGB combination. All right, double check and make sure we've got all the right ones. So this is luminance. Luminance, okay. Again, my favorite is HA for red. Just make sure we got the right ones here. HA for red. Oxygen. Make sure we got the oxygen. It'll save previous ones that you used even if they don't exist. So I like to just reselect them because it screwed me up a couple of times. And there we go. Okay. So let's keep these all even for now, but with less luminance because it'll overpower. And let's see what we get. Oops. Wrong button. Okay. There we go. And here we go. We actually have a decent image, it looks like. So I am going to modify my histogram here. Let's brighten it up. Let's see what we get when we, oops, let's, first things first. Image 05. And let's get a preview. And let's, green, see that green, if I go too far, there's still too much in the green. The green is too gray, or there's too much lightness in the green, and I need to bring that down. So I can go here and I can cut down some of the green. I don't like doing it this way, but it does work. So that's, okay, yeah, it's a preview. So let's go ahead and for now, let's go ahead and apply this. And let's minimize this. And the preview never looks good. It's just to tell you where you are. So let's kill the preview. So there we go. So these are, so this is basically how you start playing with the colors. Oh, why are you doing that? So you end up getting this beautiful luminosity and so forth. I don't like these colors at all. I would spend a lot more time working on this color. And much better. Like the red, I think this needs more red. So I can bring up the histogram again and I can bring up the preview. Put this back to where it should be. There and there. I can go to the red channel and I can, why am I not seeing the, There we go. That brought out some more of that red. But obviously this just requires playing with, and I am not very good at this software. I am brand new to this software. So I got tremendous, but that's basically it. That's how it goes. So we'll just jump back over here, see how all this is going. This is our luminosity, you know, all the way up through here. And by doing thousands of images, it just builds it up over time and develops that just beautiful luminosity. Let's see what we've got. Let's see what else is in the sky tonight. Let's see. We've got, I think we've got North American nebula. So I can stop the scripting. And let's see if we can find something exciting. So jump back over to our Sky Atlas. And so where are we now? Now is over here. Why are they? It's object type. Let's see if we've got a galaxy. Galaxy cluster. All right, we've got, so we have always got, triangulum. Let's see what we get on triangulum. Triangulum can be beautiful. So let's go ahead and just, let's set for the framing assistant, just because it lets you aim it better. If you just slew there, it's, you don't have any say in it. I don't understand why this image has a plane going through it. Why does their main, that is definitely a plane. So there's triangulum and there is framing. That looks perfect to me. Let's go ahead and slew it there. Yes. So Jackie, I think I get what you're saying. So the problem with any kind of real color with hydrogen, oxygen, sulfur, which are the common ones, is that hydrogen is sort of a mid red, and unfortunately, sulfur is like a maroon red. So you can't do any kind of true color when you're doing the narrow bands with hydrogen, oxygen, etc. But because you end up with Hubble palette, which actually I really don't like. Like, I mean, Hubble images that use Hubble palette, I really like because they're really good at it. I am not, and my images turn out like funky, unrealistic brown. So I definitely have a lot of work that I need to do in order to do that. So it looks like we're centered. Zoom out here. So there's triangulum. Let's get a nice image of this. So let's jump in and image. Let's try a 30-second image. Let's see what we get out of this. I'm trying to think of the actual frequencies. So, yeah, hydrogen is a mid-red. Sulfur is a deep red. I don't remember what color. I actually think oxygen is a blue color. It's oxygen. It's either oxygen 2 or sulfur 2, and it's sulfur 3 or oxygen 3. And I do believe it actually is a blue greenish. But I've been working with these black and white images, so I actually don't remember off the top of my head. Oh, what do we got? Is this the... I will admit that I do wish that I had a one-shot color camera that was quality like this black and white one. I do have a one-shot color, but it's nowhere near the resolution of this camera. The Triangulum is just so beautiful. I will definitely be shooting it in HA and so forth, though, because it does have huge gas clouds in it. Let's see if this changes at all. We can also move to stacking software. I can, let's see what we get here. Yeah, it's okay. So I'm going to kill this, and I am going to disconnect the camera from this software. Camera, disconnect this, and okay. And I can actually just open up different software here. And we can do some live stacking here. All right, so we're going to go to deep live stacking. Here we go. Okay, so this is the camera. So we're going to go ahead and start the camera. Good resolution, good gain. Binning is fine. 10 exposures. Let's go ahead and keep that cool to the -10. So here's Triangulum. So what it's doing is it's stacking it live. It's adding image on top of image on top of image here. Let's see what we get. I'm not seeing that image change. Am I doing anything wrong here? Oh, there we go. Let's try that. So each image that it takes, it should add on and it should improve. Oh, sorry, zoomed in too much. All right, let's let that sit for a second, see what we get out of this. So we got 5 images now stacked for a 50-second exposure. While that's stacking, I'll be right back. Oh, yeah. So, yeah, I can get, as far as the one-shot color, they actually make this exact same camera with a one-shot color bare matrix in front of it. So the only difference between this and that camera is the fact that it's got that bare matrix, that color filter in front of each pixel. So you lose actual data because each pixel can only be, well, be RGGB. So you'd have one red filter at the first pixel, then a green, then a green, then a blue. And so they can only collect that color. So you definitely, you lose quality, but not as bad as you would think. It's not 1/4 because they've got interpolation that looks at surrounding pixels and makes intelligent guesses. So you lose real data, but it does a pretty good job of making up for it. I've got a one-shot color right here. It's the one I've been using for a long time. My old camera. So this is the camera. So this is a one-shot color. But if I put this on, it just it's such the imaging sensor in it is I think this is a 3/4 size sensor. So it's a much smaller sensor and the pixels are much larger. What's up, hon?
The cats are just acting weird.
Oh, okay. Well, hey, they're just not used to people around.
Yeah.
See, what do we got there? We've got 15 stacked images there, and that's looking pretty good, actually. Like, so in all honesty, that's the best image. I mean, granted, it's black and white, but this is the best image I've ever gotten in Triangulum. I will have to. I can tell that this is all, you know, nebulosity and color within Triangulum. Let me see if I can pull up an actual color image of Triangulum.
Are you still talking?
Josh is on.
Oh, fun. Sorry.
No, you're good.
Have fun then.
Oh, I will. I'll be coming to bed soon. I mean,
Party all night.
yeah. Let me minimize that while that's collecting. Minimize this. Let's pop open Triangulum.
Like one beer, I still have a headache.
We don't drink much. I've made it all evening. I've made it through 3/4 of a beer or a hard cider. Triangulum. Triangulum right there. So this is Triangulum, and you can see the colors that are just unbelievable. See if we got any Astro Bin. Galaxy. Astro Bin. Here we go. Oh, look at that. Yeah, that is just gorgeous. Full resolution. I guess that's too much. I shouldn't have done full resolution. But this is what happens when you start taking narrowband imaging. Oh, I mean, I'll definitely do more live streams for sure. And I don't need to go yet. I do need to hit the restroom real quick, but let's jump back over here. Let's see what we got from the live imaging. Oh, let's go full screen here. That was a problem. Full screen there. Okay, so we got 29 stacked images. It didn't like one. This is what's so cool. It will eject out images that it doesn't like. So, you know, Triangulum is a neat one. It always looks a little weird to me, but I like it. All right, so I'm gonna let's find something else to image here. Let's see what else we got in the sky tonight. Jump back over here to our sky atlas, and so let's see here. So we're looking for this one's. I don't even know which one this is. Let's check this out. Let's go ahead and slew there and see what we got. So I'm going to jump down to my software here. We're going to stop this. We are going to, I'm assuming this deletes it. Yeah, clear all the stacked images. Yes. All right. Not sure why it's should be. I don't use this software very often, so let's see if we can get that imaging again. Oh, all right. Did I break it? Why is that not? Why is that not? Oh, whatever. Let's go ahead and. Okay, let's see what we get here. I'm not seeing anything yet. All right, I'm going to let that stack. I'll be right back. See, at least I'm inside, you know, so I don't have to worry about exposure. That's why I did change my desktop to red, though, because every once in a while I am down actually in the, I've got this computer that we're using that's down in the astronomy building. I do have actually what do you call it down there? A monitor and everything. I'm just not seeing anything there. I'm not sure. Yeah, I don't see anything here. So let's kill this one. Exposure's 10. See, I don't see a lot of my settings here. Well, anyhow, let us find another object. This was triangulum. This could be interesting. Let's go ahead and salute it here. Andromeda. So here's Andromeda. 13.5. 14. Okay, so they're so dim. So we're looking for something. What's this? Wait, where that? Okay. This one's bright. It's large. It's also bright and large. 60 degrees, 90 degrees, and oh, wait a second. Hold on. Let me research. I think those are up during the day. All right, try this again. All right, so 13.5, we did triangulum. This one's bright. But it's 11 o'clock, so it's going to be 30 degrees. It's a little low in the sky. So let's see if we can find something better. Oh, that's very dim. Oh, M110. This is right right with Andromeda. So we don't need to point in that one. I think this one will be okay. Let's check this one out. Oops, I didn't mean to, I meant to click slew. Let's see what we get here. So it's bright, it's big, and it should be fairly high in the sky now. Yeah, 50 degrees, somewhere in there. All right, so let's see what we get on this one. Are we done slewing? No, we're not. We're not done slewing. Uranus is up. Neptune. Oh, Saturn. You know what? I'm thinking we should try to image Saturn, see what we can get on Saturn at some point here. Let's get some images on this and then put Saturn. And if nothing, then we'll call it an evening. Yes. All right, I'm gonna hit the restroom. I'll be right back. Hi, Kat. Oh, look at that. Look at that's pretty. Holy crap. That is an edge-on galaxy. That Hun, take a look at this. Okay, then don't come look at this. Yeah. Yeah. Wow. Okay, I'm writing that one down. Hold on a second. Let me get a pen. Well, I could just use my board. Okay, so this was that's pretty cool. All right. What did I just hit? Where am I? I need to go here. That was NGC 891. Write that down. NGC 891. That's a future target to be hitting. All right, let's hit Saturn. Let's see what we can get out of Saturn. So what I'm going to do is I am going to stop this because we're going to go to a solar system object. So kill that. Yes. Close. We're going to kill this. We're going to open this guy up and go to Saturn. Okay. So give it a second to calm down. Let's go back to our ASI software. And this is going to be our planetary imaging. Okay. I'm going to go to our 6200. There's Saturn. All right. Wow. So I am the focal ratio of the scope for this right now is so I'm trying to think. The pixels, I've got such a wide angle that's why you're seeing it's so incredibly pixelated, because that is literally each pixel. But you can see we've got a start there. Let me see if I can get the autofocus to run. So I'm gonna stop here for a moment. I'm gonna kick back over to N.I.N.A. We're going to reconnect up here. And let's turn back on the cooler again. Let's get that temperature. There we go. So that's going. And there's some software I've downloaded here. It's the Lucky Imaging. Show every 10th image, minimum available memory. Let me take a quick read of this. Oi. Yeah, I don't know that this is going to be what I want, but let's anyhow, let's kick over to here and let's go ahead and do a I want to do an autofocus real quick. So let's go to focus. Oh, sorry, autofocus. Let's get an autofocus going here. Hey, Jackie, if you're still with us, I'm actually hanging out with Devin tomorrow. Well, Monday. Corey and I are going to hang out with her in Denver. I suspect Saturn's off the image here. I think that this is going to be Saturn right here on the edge. It's odd. The stars seem fine to me. Let's try that again. Why is it always something? Why are you only, it's working perfectly. Why is that giving up like that? Oh, the frustration is real. Well, I mean, it's pretty good focus. Let's see if we can, so under mount. Oh, you know what? I can just do this. I can cheat telescope slew controls. So let's see which direction we're at here. So let's get the imaging, and we're just going to take 1 second because we don't need much here. that's not Saturn. Okay. Oh, so Saturn is not in view here. Why is that? Okay, comets, James Webb, solar system body, Saturn, load. All right, let's see if that works. And it may be, Jackie. You may be right. It's normally not that dramatic. It normally is. I'm trying to think of the right way to put this. I find that the cooling is more just kind of a noise generation, and the autofocus still works usually, but it could be. Like I said, this is a brand new setup to me, which is why the previous nights I've had good luck because it's basically been imaging the same objects night after night, and which makes it easy. And now I'm kind of doing stuff all over the place. So I don't know. It just a little bit of a frustrating night. Like everything seems a little off. The N.I.N.A, this software that I'm using, it's brand new for me. I've only been using it for 2 months. Just while trying to calibrate everything. So it seems to think it's there now. Let's see if we can get something. So yeah, I'm. It's just frustrating. Wow, that is right. Okay, so what I'm going to do here is I am going to, it says that we're on Saturn. So I'm going to kill this and go back to our imaging down here. And let's get this kicking again. Why am I not seeing anything? There we go. Hey, we have a moon. Let me go here. So the next thing I know, I need to go and tell this Saturn. It helps with the exposures. Oh, it's got the electronic autofocus going on here. So let me disconnect the autofocus from here and see if it will if that'll work. I don't do much planetary. So this is again new software, new ways of doing stuff. So let's go ahead and connect to the autofocuser. Current position. Yeah, this is all correct. Good. All right. Okay, so we're there. We're on Saturn. Okay. Let's see here. Is there a focus setting here? I don't see a focus. I see a filter wheel. Is that focus? Oh, it's a manual thing. That is definitely Saturn, though. And I can see at least 2 moons. I can't tell if that's improving or making things worse. It's definitely overexposed. So let's drop down our exposure. Oh, there's still a moon there. Okay. Ooh. Saturn is so bright. Oh, that's definitely worse. Yeah, I can't tell. What I'll do, Josh, is I'll set up so in prime focus, which is where the camera is at the very back of the scope. It's got a lot more essentially zoom. So my focal length, instead of like right now, my focal length is 715 millimeters. If I go to prime focus at the back of the telescope, it's 3,000 and some millimeters. So it's much better image. Yeah, that's worse too. I like seeing those moons. Let's see if we can get those moons to pop again. But we can. This scope is capable of pretty incredible views of Saturn that I've seen. So knowing that Saturn's up at 11 o'clock, where are those? Let's see if we can really get those moons to pop by overexposing this. So there's a moon there. But this configuration here is really for deep sky stuff. Nebulas. There are the moons. Look at those. Looks like we got some moons here too. That I suspect is a moon. Yeah. We got a moon, we got a moon, we got a moon. Oh, too far. That could be a moon. Yeah. So I'll reconfigure it so that we get that. But yeah, these we're just too zoomed in here. So let me kill this. Trying to think let's see if there's anything else that's jumping out. Pluto's low on the horizon, but Pluto's right there. What are you? Oh, the Pleiades. Let's go to the Pleiades. Let's see what we can get. I'll bet it doesn't work. I'll bet I take a picture of the inside of the astronomy dome. What are you? NGC 884. What's NGC 884? NGC 884. Open cluster. All right. Not the most exciting thing in the world. All right. Let's see if we get anything here. Or I'm fine at 13 degrees. That looks like a satellite, which surprises me. It's too late really for satellites. What did I just go to again? Ah, the Pleiades. So here they are, right here, the Pleiades. Yeah, I've never been a huge star cluster kind of guy, but you know. So let's see if there's anything else exciting going on up here. That was that one. Let's see what we got. Oh, unlock that. So here's Andromeda. It's quite interesting to be able to go outside and see Andromeda like with the naked eye. Let's take a look at what M39 is. It's not. Oh, it's a star cluster. Yeah. Hmm. Hmm. All right. Let's see what we got here. So looking south. So there's Saturn. Okay, yeah, we got our deep space objects. All right. Oh, here we go. Here's the Milky Way. We've got let's go to the North American Nebula. That can be fun to shoot. Let's go to framing. Pull it from there. It'll take it a second to load it. Still high in the sky. Let's see, where do we want to aim this? Right about there. That's probably pretty good. Let's go ahead and Head that way. Okay. Looks good. That is definitely the North American Nebula, though. It's going to move it around a little bit, but so we're off by 3 minutes. Not very much. Okay, so it's on target now. Let's go ahead and take some images. Yeah, it's so hard because I do need to see. Maybe I'll hook up the color camera at some point the next time, or at least in the meantime, and see what it looks like when you with this camera that I've got, the color camera that I've got, to see if we can get some good images with it that are color. Because what I'm realizing is for me, I know what this looks like, so I can see the nebulosity and know what colors and what it's about. But for someone that's not familiar with it, the black and white image is just not as exciting. But that's not bad. I mean, it's beautiful, but not as impressive until you get the images and you get them thrown together. So, all right, folks, I think I'm going to give it a call. All right, Josh, have a good night. Jack, if you're still on, have a good night. Oh, no. There. Everyone's off. Hey, I'm glad you joined, Josh. It was fun. So I'm crashing hard though. I will see you in the I'm off Monday. So I'll see you Tuesday, my friend. Have a good one, and yeah. Take care, my friend.